Okay, so it's 9:15, so we can start the first Attochem Young Scientist Symposium 2021. So welcome all. Good morning or good afternoon, depending on your time zone. My name is Gabriele Crippa. I'm a PhD student from Politecnico di Milano, working in a group of Professor Salvatore Staggira and Professor Caterina Pozzi, and I'm also the local organizer of this event. Unfortunately, due to the coronavirus pandemic, we were not able to organize this event in person and to host you here in Milan. But we anyway hope that you will enjoy also this virtual format. So in order for you to take out the most of this event, we encourage you to ask questions to our speaker, to try to maximize your interactions with them, also with discussions. And before starting with, let's say, some organization details, I would like, on behalf of all the organization committee, to thank the European Union, in particular, the European Agency for the Cooperation in Science and Technology COST, and the Attochem network for giving us the opportunity to organize this event. And I would like also to thank you all the participants for registering and all of the scientists that decided to present their work at this event. The number of submissions was really outstanding. We didn't expect it. Also, participation is very high, so we're really, let's say, happy about it. So before going on, I would like to give the stage to Professor Fernando Martin, who is a professor from Universidad Autónoma de Madrid, and he is also the chair of the Attochem network. In a brief speech, he will present you this Attochem action, and in particular, all the tools that this network gives to young scientists in order to foster their research and their career. So, Professor Martin, if you want to join.
Thank you, Gabriele,
the stage is yours.
For the introduction. Well, first of all, I want to thank you and all the organizing committee for implementing this experiment. That is the first time we have such a meeting in the Attochem network. I have to say that this meeting has been entirely organized by young researchers at the PhD level and young postdocs. They took all the responsibilities. The format is their choice. The speakers is their choice. The way it's done is entirely their choice. So I'm extremely glad that you did it. I think you were able to convince a lot of people to attend. You have an outstanding program. And so I want to congratulate you in advance for this. The role of the Attochem network was just to provide the financial tools, nothing else. So I see that you have used them very well. I also want to thank Eva Vrezinova, who is the early career investigator manager, and she's the one who was, who had the idea and who really encouraged and looked for people who could do this. So I'd like to, since I understand that many participants are young and probably are not aware of the Attochem network, I'd like to say a few words about it. So I will share my screen briefly and show you what Attochem is for those who do not know, and how you can use the different tools. So basically, in Attochem, the purpose of the Attochem network is to design Attosecond-like pulses and Attosecond control strategies that can be used to induce charge migration dynamics in molecules, either isolated or in solution, and so that you can, induce some new chemical reactions. That's the main objective, very, very general. And this is achieved, we try to achieve this by working in 3 groups. The first one is mainly experimental. It's about the development of new Attosecond techniques for the control of electron dynamics in molecules. The second group is mainly theoretical. So it's about the development of computational tools for the description of these dynamics at the Attosecond timescale. And finally, there is a third group that is more directed to applications of the above tools to image and control charge migration and chemical reactivity. So the interesting part for you is what you can do with Attochem. So in Attochem, we support meetings like general scientific meetings now of the whole action. And the next one is very soon, in a month, in October. So I encourage you to go to the Attochem website and check how to register and see the program. We can also support working group meetings, so meetings, restricted meetings, so to people working in a specific working group. And we can support, as we have done, young scientific symposia. That's why we are here. And this is the first one we organize, and we hope this will not be the last one. Okay. We can also support training schools, also to help young researchers to learn about, different techniques that could be useful for the development of their PhD thesis and their postdocs. And we also organize and support Attochem webinar series. And we are finishing the first series of them, and there are still 2 that will take place the 22 and the 29 October. A very interesting point for young researchers is that we can support short-term scientific missions. And that means that we can fund scientific stays in different laboratories, from people trying to go from one country to another just to collaborate or to develop a specific research project. Another thing we have is ITC conference grants. So these are grants that we provide to researchers working mainly in Eastern European countries. So, and these grants cover, travel expenses and registration fees to attend conferences. Now, since most of them are virtual, we also cover, registration fees for virtual conferences. And we have a new tool that is virtual mobility grants. And these are grants that provide support to organize online activities to online collaborations. And again, you can find the information about these tools in our website. So here you have the links. You have different email addresses where you can send emails asking for questions or information. But in general, I would say that please visit our Attochem website, and you can see the details of all this. I encourage you really to apply for these things, and because I think they are extremely useful, and especially for young researchers. And the people who are organizing this network are basically, well, apart from me, who I'm chairing this, but Francesca Caleugari is the vice chair of the action. And we have, sorry, because my mouse is doing things. We have our STSM coordinator, Bernard Pirot. He's responsible for gathering all the applications for short-term scientific missions. We have, as I said, Eva Brezinova as the early career investigator manager. We have a gender balance manager, Violeta Petrovich. And we have the ITC grant manager, Annette Liebok. And a very important person is Aurora Ponzi, who is taking care of all the scientific communication and dissemination activities of the action that nowadays have become so important because most things now are done online. And finally, we have the coordinators of the different working groups. Katerina Bozzi, working group 1 is the experimental one. Laudislau Nagy, working group 2, the theoretical one. And Frank Lepin, the applications group, working group 3. And we have some advisory board coming from abroad, from the US, Luca Argenti, Ludi Mario, Yoshi Ueda from Japan, and Monica Garcia from Spain, and Thomas Melzer from Germany. And finally, let me say that this gives you the map of the action. So the countries that actively participate, we have 26 countries now participating, and as you can see, it's a very international network, and I hope that you can join and participate. So please go to our website, look at the information, and if you are interested in these activities, please register in our website. Thank you very much.
Thank you, Professor Martin, for this nice and also useful presentation. So before going on with the first session of today, I would like to remember you some, let's say, technical and organization details. The first 3 days of this symposium will be organized in a morning and an afternoon session. Each one of these sessions will be opened and closed by an invited talk of 40 minutes, including the question. And between these two talks, we will have 4 talks by usually, let's say, early career investigators or PhD students, which are the core of this event, and will be of 20 minutes, question included. In the middle of each session, we will also have a coffee break of 20 minutes in order to restore energies, let's say. I remember you that on Wednesday, the last session of the afternoon will end at 4:20 instead of 5. And that's because, let's say, an invited talk is missing, unfortunately, got cancelled. After the afternoon session, we will have then a poster session, and this will be organized in 2 moments. In the first one, each poster presenter will give a brief presentation of the main idea of their poster. This will be a 5-minute presentation without any question time, and all these presentations will be done in a strict sequence. After all these series of presentations will be over, then the speaker, so the poster presenter, will be divided in breakout rooms, each one assigned with their names. So for participants, it will be easy to, let's say, orient between them. And participants will be able to join freely each one of the room, to switch between them in order to discuss with the poster presenter about their work. Inside this breakout room, the poster presenter have also the opportunity to share other, let's say, material that maybe he or she did not have time to present during their talk. On the last day, instead, we will have just the morning session, and this will be divided in 2 parts. In the first one, we will have another, let's say, poster session, while after a small break, we will have a roundtable discussion with 4 scientists at different stages of their career. And this is meant to be, let's say, an informal moment in order for participants to ask questions both on scientific, let's say, topics, but also to non-strictly scientific and technological topics. For example, about their view on attosecond science, future trends. They will be able also to ask for advices maybe for their career or how to get fundings. Indeed, some of these scientists has also let's say, received the ERC grants, so they are the right person to ask for this question. And we really hope that all the young scientists participating today will get, let's say, the most out of this roundtable. We think this is a really important moment, so we really encourage you to participate actively in it. I remember you just the last things, that when accessing every room session with your personal link, your microphone and your video will be automatically switched off. Please maintain them off during all the session in order for the session to go out smoothly, and switch them on just when the chair of the session gives you the stage, if you're a speaker, in order to give your talk, or addresses you in order to ask for a question directly to the speaker during the question time. For the other part of the sessions, please maintain both the microphone and the video off. We remind you also that all the sessions will be recorded and will be uploaded on the YouTube channel, official YouTube channel of the Attochem Action after the end of the symposium. So you can access them also on delay if you missed something or you want to, let's say, relook at some talks. Of course, every speaker is able to opt out of this option. So if you wish your talk not to be uploaded on YouTube, please just notify it to us through email at the official email of the event, which is, I remember you, atto.yss2021@uam.es, or write an email directly to me or anyone else of the organization committee. I would like also to notify you that, unfortunately, yesterday we uploaded a book of abstract that contained some errors. So today we uploaded a new version without any errors. So you can download the new book of abstract, that is the correct one, from the official, let's say, website of the event. In this, I think I said all the technical details that were, let's say, supposed to be told you. And we can go on with the first session of the day. which will be about the ultrafast dynamics and spectroscopy of molecular and of atomic and molecular systems. And the first speaker of the Young Scientist Symposium and of this session will be Professor Henrik Stapelfeldt from the University of Aarhus. And he received his PhD in physics from Aarhus University in 1993. Then he spent his postdoc in Canada, in particular in Ottawa, in the group of Professor Paul Corkum. And since 1996, he was assistant professor at the Department of Physics of Aarhus University, where from 2009 holds the position of full professor. From 2013 to 2018, he managed an ERC advanced grant for the control and ultrafast imaging of molecules in helium named droplet control. And his research activity involves the manipulation and study of molecules with short laser pulses, orientation of molecules, and the ultrafast imaging of reaction dynamics. So, Professor Stapelfeldt, the stage is yours, and
so thank you
for joining us.
So first of all, do you see my screen or do you see my notes?
Yeah.
The real screen?
We see everything.
That's fantastic. Then I just need to get this one. Wonderful, thank you. So first of all, thank you to the young organizers of this symposium. I look very much forward to talking to you about first fundamentals of how you align molecules, both in the gas phase and in helium droplets, and there will also be some recent applications. So as a start, I would like to tell you what I mean by alignment of molecules. And alignment of molecules means that you confine axes of molecules to axes that are fixed in a laboratory. This is shown here for the simple case of linear molecules and a single axis along the vertical direction. Let's see if we can regain momentum. So this is more or less where we came to saying that you can align molecules, and this means that you confine axes of molecules to axes that are fixed in the laboratory. And this stands in contrast to the usual situation that we encounter for molecules and gases on liquids. And the kind of alignment that I show you here, we call one-dimensional alignment because it's just a single axis that's being aligned. That concept can also be transferred to much more complex molecules. But if you look at molecules like the one I point to here, you can see that if you would like to obtain full three-dimensional control, you would like to confine all three principal axes of such an asymmetric top molecule. And in that case, we call it three-dimensional alignment. And even then, for a molecule like this, which is polar, then you would like to sometimes at least also have all the pink noses point in the same direction. So you'd like to obtain what we call orientation. So for such a system that's both oriented and aligned, we call it 3D orientation. And this is clearly also a concept that you can extend to or apply to linear molecules. We call it 1D orientation. In this talk, I'll actually mainly be speaking about one-dimensional alignment. However, it turns out that laser pulses, sometimes in combination with weak static electric fields, can actually achieve all these different alignment schemes. So having told you about what alignment is, of course, I should also try to motivate why we're interested in aligning molecules. And there are two major reasons I'd like to share. And the first one is sort of the historical one that came from chemistry 70, perhaps even 80 years ago. And that's the simple fact that interactions between molecules, reactions between molecules, depend on how they are turned in space. And this is, for instance, the case when you look at the reaction between two molecules, or an atom and a molecule. And if you're able to align or orient your molecules in space, then you can in principle test, for instance, if textbook on organic chemistry are right when they claim that chlorine attacking methyl iodide from the end here is the reaction geometry that favors a so-called SN2 reaction rather than the perpendicular geometry. However, nobody have ever done this experiment. The orientation or the alignment dependence is also very much present when you look at interactions between molecules and polarized light. In particular, which is relevant to this community in attosecond science, if you look at the interaction between intense laser pulses and molecules, interactions that could, for instance, be high harmonic generation above threshold ionization, then it's also possible, and people have been studying this for 10, 15 years, to study such alignment dependence or even exploit it to do, for instance, tomography. The other major reason why it's of interest to align or orient molecules is the fact that you get access to the molecular frame rather than the laboratory frame. So you can measure things that happens as the molecules see them. And this enhances the information from the experimental observable that you can extract. And just one example that I've been sufficiently immodest to pick from my own group, an old experiment that we did 12 years ago, is when you photoionize molecule and record the emission direction of electrons. And if you do this for randomly oriented molecules, then you can obtain a velocity, a two-dimensional velocity image of these benzonitrile molecules that happen to be ionized by circular polarized light, polarized in the vertical direction, or along the vertical direction. And you see this nice image of the electron that come out along the polarization direction. That's great. However, if you pre-align, actually 3D orient these benzonitrile molecules prior to the application of the ionizing pulse, you can see that the electron images changes quite significantly. And all of a sudden the structure, there's these kind of rapid ears, and this essentially means that you can extract more information, in this case, about the orbitals that the electrons are removed from. So this is an example where you really benefit from the ability to fix your molecule in space. So now we know what alignment is, we know why it's interesting to align molecules, and of course we have to ask the question, how do you align molecules? And this is a small molecule, this is OCS, carbonyl sulfide. It's actually a polar molecule, so it has an excess of negative charge here and positive charge here. So you might think, so such a molecule has a dipole, a permanent dipole moment, and then perhaps the most obvious thing to do is to put this into a static electric field, because what the molecule wants to do in the presence of the field, wants to minimize its energy, and it does so by pointing the dipole along the field. Much in the same direction as, you know, if you're out hiking and you use an old-fashioned compass, not a modern GPS, and of course the magnetic dipole orients with respect to the magnetic field of the Earth. So this electrical analog of the compass requires that the interaction energy, so this is the product of the dipole and the field, exceeds the rotational energy significantly. One way to ensure this is to lower the temperature, but even if you do this, you still require a very strong electric field. And this is not so great very often, because what happens, and people that have tried to do these things knows that no matter how careful you are by polishing the electrodes, you will typically get electrical breakdown, so you get sparks. So this is not good, you lose your electric field. Moreover, if you deal with a molecule, for instance, like our beloved CO2 molecule, the ultimate villain of all molecules these days, doesn't have a dipole moment. So an electric field won't orient or align this molecule. So that's not so great. So what we can do instead is you can actually replace the static electric field with the electric field from a strong laser pulse. Now, strong laser pulse can be so strong, many of you know this much better than I do, that you can induce very large dipole moments. So even if the molecule is unpolar, it doesn't matter, because the electric field just induces a dipole moment. And this will happen to any molecule, because all molecules contain electrons, so all molecules can be polarized. And this induced dipole moment will now minimize its energy by aligning with the electric field of the laser. Of course, you know that laser pulses are electromagnetic waves. So the situation I considered was, for instance, at this instant of time, but half an optical period later, you know that the electrical field will turn in the other direction. So this is what happens 1 femtosecond later here. But at that time, the induced dipole will point the other way, but it is still going to induce a torque that forces the molecule to rotate along the axis of the polarization vector. So this is the basic idea of what we are using in our work. We use a moderately strong non-resonant laser pulse to align molecules. And on the next slide, I'll show the interaction and expression for this, but let me just dwell for 2 seconds with these words. Moderately strong, well, strong, we want it strong, because if it's not strong, then there won't be much alignment, because you require quite a strong dipole. Moderately simply means that we have to keep it sufficiently weak that it doesn't start to ionize the molecules or dissociate or do other things. So we want it only to align. So there's an upper limit to how large field you can apply. So we want to turn off nonlinear interactions other than those that lead to alignment. Non-resonant means that we want to stay away from frequencies or wavelengths that leads to linear absorption. And in practice, we do this by using infrared laser pulses, typically around 800 nanometer or 1 micron or 1.3 micron. So let me give you a few more details about the theoretical background for how you do these things. So the induced dipole interaction or polarizability interaction, if you like, can be written like this. So this is a product of the dipole moment and the laser field, and it's given by the intensity of the field squared of the laser times the polarizability anisotropy. It's the difference between polarizability along and perpendicular to the axis. I should say I'm just looking at a linear molecule in a linear polarized field, and then times cosine squared theta, where theta is the angle between the molecular axis and the field. And that potential energy is plotted as a blue curve here as a function of the angle. And you can see there's a minimum at 0 and at 180 degrees, which basically, I don't know if you can see my camera, I hope you can, but that means the molecule wants to be like this or like this, as you could expect. So what this potential really does in a classical sense is that it converts freely rotating molecules into molecules that are librating, so showing this kind of pendulum motion, and the amplitude of the pendulum is determined by the initial rotational energy. So if you have a low rotational energy, you get sharp alignment or sharp confinement. If the molecule is rotating very rapidly, the laser field is not able to confine it so greatly. And of course, it also helps if you can turn up the intensity of the field strength. So the deeper the well is, the more confined you get your alignment. This is speaking classically. Of course, what we do quantum mechanically, we take and solve the time-dependent Schrödinger equation, where you have the rotation energy, it's just the angular momentum, the rotational angular momentum operator squared, plus the interaction with the induced dipole, and then you solve this one, and I can do this on my computer quite easily. And the solution can be expressed as a linear combination of eigenstates, rotational eigenstates. If this is a linear molecule, this is what we call the spherical harmonics that you can look up in any textbook. And in general, the coefficients, the expansion coefficients of the eigen functions are time dependent. So this is what we call a rotational wave packet. So this is a superposition of eigenstates, and this is why you can confine something angular, much like when you mode lock a laser. If you want to make a short laser pulse, you need to make a superposition of the eigenmodes within the oscillator. In order to characterize alignment, there are many ways you can do this, but a standard measure in the literature is what we call this expectation value of cosine squared theta operator. It's defined like this, and I'll refer to this property a number of times. It's 1/3 if the molecules are randomly aligned, and it's 1 if they are perfectly aligned, and 0 if the molecules are what we call anti-aligned. So I want to show you an example, and this is a calculation of alignment of a sample of OCS, carbon sulfide molecules, kept at a temperature of a Kelvin and aligned with a 600 picosecond pulse. And this is the red curve. This is the envelope of the field here. So this is intensity, and I think the intensity is about 5 × 10⁻11 watts per centimeter square at the peak. And it turns on slowly, and here slowly means slow compared to the normal or the inherent rotation period of these OCS molecules, which is about 80 picoseconds, entirely determined by the structure. And the black curve now shows you the degree of alignment. As I told you, it starts at 1/3. This is expectation value of cosine squared theta for randomly oriented molecules, and then it grows sort of perfectly along with the field, and then it peaks, reaches a peak at the peak of the laser field, and then it essentially drops back to where it started. So you can see here, illustrated by the small diagrams here, that before the laser pulse, molecules are randomly oriented. At the peak, it's nicely aligned, and after the laser pulse, the molecules return to where they started. This is the adiabatic behavior of alignment. This is very useful for many experiments, and I'll show you how we do this in the lab. By contrast, on the opposite regime, we talk about non-adiabatic alignment, which you can achieve when you have a very short laser pulse, much shorter than the rotation period, and I'll also show you how this is done. So, so how do we measure alignment? This is something we also need to be concerned about, and the simple way to do this that we've done for many years is to Coulomb explode the molecule. This is illustrated here for a diatomic system. So essentially you have an intense laser pulse that comes in, strips off a number of electrons, you remove the glue of the molecule, and it breaks apart into ionic fragments, and the ionic fragments recoil along the bond axis. So measuring how the molecule is aligned basically boils down to measuring the emission direction of atomic or molecular ions, which is something that there are very strong experimental instruments available for doing. So that this works is probably obvious for a diatomic molecule. It turns out that in many cases it also works very well for more complex molecules. And when you deal with complex molecules, you're often interested in recording not just one ion species, but several. And today there are fantastic cameras, detectors available that can record all these fragments at the same time. So you get an enormous amount of information out from the experiments. So how do you do the experiments in practice? Well, this is a sketch of the setup that we use in our lab. So the molecules are formed by supersonic expansion, and this is now looking concretely at iodine molecules. You can see these little iodine molecules down here. So, so we expand a gas of iodine molecules seated, for instance, in helium, and the resulting molecular beam becomes rather cold in terms of rotation, 1 or 2 Kelvin, and it travels to an interaction region where it's crossed by at least 2 laser beams. The first one here, marked by this rainbow color, is a 160 picosecond pulse, which is going to act in order to induce adiabatic alignment. It's not quite long enough to ensure perfect adiabatic conditions, as you'll see, but it's all right. And then we wait for a while, and then after a controlled delay time, we send the second pulse, which is the one that causes Coulomb explosion, produces ions, and these fragment ions are mapped onto a 2-dimensional imaging detector, and with a camera, for instance CCD, but we have much nicer cameras now like the Timepics that can record 2-dimensional or even 3-dimensional images of these ions. So this is a basic experimental information we get out. And I'll immediately show you, I can see I lost my mouse now.
That was the last time we had 21 output, right? So
see problems with this computer today. That's unbelievable. So I hope you can see my screen again now.
Yes.
This is not the best day, but I'm doing what I can. Let's continue. So I think you should be able to see an image here. So this is now an image of where we look at iodine molecules. This is an image of the I+ ions resulting from Coulomb explosion recorded in the absence of alignment field. So just with the probe field. And you see an image that is circular symmetric, which essentially tells you that the molecules are randomly aligned, as you would expect. Now, when you include the alignment pulse polarized vertically, you see that the image changes rather dramatically, and it confines, the ions are now confined along the polarization vector of the alignment pulse, which tells us that the molecules are being aligned. And in fact, the ions recorded between the 2 white annotated circles are the one that stems from Coulomb explosion. So those we can use to extract the degree of alignment. And that's what I show you on this page here, on this slide. So you can see the degree of alignment versus time. The gray shape here is the alignment pulse, or the envelope of the alignment pulse, and the blue curve is the degree of alignment. And just as I sort of indicated on the theoretical calculation you saw before, OCS, the degree of alignment follows the envelope of the alignment pulse. It reaches a peak at the peak of the alignment pulse, in this case about 0.9, which is quite a good degree of alignment, and it drops off as the laser pulses turn off. So this is the adiabatic behavior of or the adiabatic regime of alignment. So I'd like to show you something else, going to quite the opposite regime. So rather than using this 160 picosecond pulse, we can take a pulse that is much shorter, namely just half a picosecond. So essentially cutting down the pulse duration of the alignment pulse by a factor of 200 or 300 or so. And now we enter the non-adiabatic regime, but the experiment is the same. we record ion images as a function of the time delay between the alignment and the probe pulse. And this is an image now, sorry, not this is an image, this is a process data. This is degree of alignment versus time, and the red curve here is the experiment, this is a calculation. So now you see the dynamics is really strongly different from what you saw in the adiabatic regime, because now essentially all the dynamics occurs after the laser pulse is turned off. So you see shortly after the pulse, the molecule reaches a maximum. This takes a little time to occur after the pulse. This is because the molecule has inertia, so it takes time to rotate into alignment. Then it loses its alignment, but now it recurs at later time. And these transients are called revivals. This is a so-called half revival, a full revival. And this is a consequence of the fact that the alignment pulse induces a rotational wave packet. So experimental observables become time dependent. And this is what you see here, half and full revival. The periodicity of this alignment trace is determined by the structure of the molecule, so by its rotational constant. And it happens that for iodine, which is a rather heavy molecule, that the revival period is about 500 picoseconds, 446 to be precise, and it's given by 1 divided by 2 times the rotational constant of iodine expressed in Hertz. If you increase the alignment pulse from 6 times 10 to the 11 to 1 times 10 to the 12, you see the same. However, the modulation of the alignment trace becomes more pronounced, but the structure remains the same. And this modulation increases, and the degree of alignment increases, and the transient sharpens as you increase the intensity of fluence further. And you can see that here. Now, if you dwell at this half revival for a minute, then you can see that about 220 picoseconds after the laser is turned off, so the laser pulse is completely off, you actually have a quite strong degree of alignment of about 0.85 under completely field-free conditions. So this is one of the reasons why these rotation wave packets have become quite popular in the femtosecond and even attosecond community, because you get access to rather sharply aligned molecules completely without any perturbing alignment field present. You can use this if you ultrafast, so you have about perhaps 1 or 2 or 300 femtoseconds at your disposal where you can do experiments. And this has been used in many experiments for strong field ionization, high harmonic generation, various nonlinear objects. If you continue to increase the intensity of alignment pulse, you see that these transients sharpen even further and further and further and become really, really sharp. And now I can't go higher, because if I increase the intensity of the fluence higher, I'll start to ionize the molecule. So the reason that you see these transients becoming much sharper is the fact that the alignment pulse drives the population of initial rotation states higher and higher up along the rotational ladder. And this leads to faster dynamics, because the dynamics is essentially determined by the energy difference between neighboring rotation states, and that gap increases as you go up in J, as you will know if you have studied molecular physics or physical chemistry. So this is a summary of all these traces you saw. It's overlaid, the experimental results are overlaid by theory, so I mean, I don't know if you can see it, but they actually fit nicely. But perhaps what's interesting for you to see is that each of these traces can be Fourier transformed to retrieve the spectrum. And for low intensities or low fluences, you see that the spectrum is restricted or confined at rather low values. But as you increase the fluence, so this is going here and here and here, you see that the spectrum shifts to a higher value and it broadens. So this is a direct way to see that the alignment pulse drives the population up to higher and higher rotation states, and also shows you actually the wonderful aspect of non-adiabatic alignment as a spectroscopic tool. So you can actually do very high resolution spectroscopy by means of these almost a comb of rotational energy beats. All right, so what I've shown you so far is in fact only the rotation dynamics for the first rotation period from 0 to about 500 picoseconds. But if the molecule is in gas phase and nothing perturbs it, then in principle this rotation dynamics will just go on. And you can see that here on this little animation of an experimental experiment, it's almost, for me, this is almost like a heartbeat. of the molecule that you see. And some of you that do experiments may say, oh, okay, these guys are actually not so great experimentalists, because you can see that the amplitudes of these rotational revivals decreases. So it's like when you increase the delay between the alignment and the probe pulse, they may lose the spatial overlap in the experiment, and thus, I mean, get short of signal. But this is actually not what happens. And although this is kind of a special thing, then I just want to point out that it's not like we are measuring incorrectly. If you do a simulation and just assume a free rotor, then you would get the gray curve here. This is a calculation. But if you include the fact that the rotational angular momentum actually couples to the nuclear spin, then you get the red curve here. So this is a calculation taking this hyperfine structure into account. So that means that these rotational wave packets are in fact also sensitive to something like hyperfine structure. So this is something that's particularly pronounced when you have iodine, which has a large electrical quadrupole moment of the nuclei. All right. What I've shown you so far in order to characterize alignment is this expectation value of cosine squared theta. And it's actually not such an amazing observable in the sense that it only shows average properties, but in fact, there's much more information available. I thought I'd just play, let's see, now I have to get out of this one. So I thought I'd just play you a movie of the images that we record when we do these experiments, because it turns out there's much more information available. So this is now an experiment, not on iTube, but on OCS. This was a collaboration with Mark Fracking and Jochen Küpper, carried out a few years ago. And I think it's a rather nice movie because you can see the real alignment dynamics. Maybe I should just pause it for 2 seconds. So what happens is that there's one laser pulse being sent at time equal to 0, and then there's a second laser pulse coming in at about 30 picoseconds, maybe a bit later. And then you can see this really, really rich dynamics going on with alignment and anti-alignment. See, this was, okay, I think I just stopped it. So this is where the molecule sharply anti-aligns around 23 picoseconds or so. And if you continue the movie, you'll see that after pulse number 2 kicks in at about 35 picoseconds, shortly after that, you see, yes, I caught it here, an incredibly sharp alignment. So this corresponds to this point here where the OCS molecules reaches something like 0.96 in degree of alignment, so almost perfect alignment under field-free conditions. And the movie goes on, and it's quite nice. So, and you can read more here if you're interested in this. All right, let me see if I can get my mouse back here. That was right. So, laser-induced alignment is a rather mature field. It's been on for, I think, 25 years, actually, perhaps even a bit more. And there are many, many applications of aligned molecules, high harmonic generation, chemical reaction dynamics, nonlinear optics, photoelectron angle distributions, chemical reaction dynamics. And I could show you lots of these applications. I'll show you 2 slides. One is from my own lab. This is something we did quite some years ago now, but it shows you what you can actually learn of new stuff if you pre-align the molecules. So this is an example where we looked at an intermolecular vibration of a rather complex molecule. This is this biphenyl molecule. And by fixing this molecule in space, so it's actually convenient to look at this from the end, then you could initiate torsion. So this means sort of twisting between the 2 benzene rings with a laser pulse. And then you could image this torsion by Coulomb exploding the molecule and recording either bromine, this is a red guy sitting here, and the fluorine ions, and then measuring the relative emission direction between the fluorine ions and the bromines. And the only reason that this works is because you can place the molecules in a favorable view with respect to the imaging detector and thus get the full information out. So in a way, this is a molecular movie of torsion. This is an important intermolecular motion because it connects the left-handed and the right-handed enantiomer of this chiral molecule. And you can see that this torsion here measured in real time occurs with a periodicity of about 1.2 picoseconds. In fact, we could play the movie all the way out to 100 picosecond and see how the torsional wave packet dephases, etc. The other example I've just very quickly mentioned, because I think there'll be other people speaking about similar stuff at this meeting, is, as Fernando Martin mentioned in the beginning, this is charge migration, and this is an experiment. So this is something that's very important for fundamental aspects of light absorption in molecules. Is one of the primary steps that happens after molecules, also biological molecules, absorb light. And this was an experiment that was carried out by the group of Hans-Jakob Werner 5-6 years ago, where they used alignment and orientation techniques to orient this iodoacetylene molecule in space. And then they did high harmonic generation from the scatter molecules, and using the spectrum of high harmonics, they were able to actually reconstruct the relative population and phase of the different orbitals that are involved in this ionization process, and essentially do this as a function of time by using the different orders of the high harmonics. So in a way, look at charge migration, or reconstructed charge migration, as a function of time with essentially sub-femtosecond time resolution. It's a beautiful experiment. Okay, if I still have a little bit of time left, and I hope I do, I would like to show you a little bit about what we are really interested now, so where we're going. And the field on alignment, and also what I told you so far, has been focused on isolated molecule in the gas phase. And this is of course very interesting, but what we're doing now, and I try to tell you why we're doing this, is we are putting molecule into a solvent, not the solvent of water or methanol or aceton nitrite or something like this, but a rather mild solvent, namely helium, liquid helium. And we do this by embedding or solvating molecules in small droplets of liquid helium, so what is called helium nanodroplets. And these little droplets in our laboratory contain about 10,000 or less helium atoms. They have a size up to 10 nanometers, and they're cold, or at least relatively cold. They have a temperature about 0.37 Kelvin, and they have superfluid properties. So experimentally, you already saw this this slide, and you would probably recognize that there's all this white space. And this is because we have something else on our instruments. We namely have a beamline that can produce these helium droplets. And this is done by expanding a cold gas of helium, so cooled by a cryocooler that you can buy, down to 10, 20 Kelvin or so. And when you do this and you blow this cold helium into vacuum, do an adiabatic expansion, the helium becomes so cold that it condensates and it forms helium droplets. And these droplets are then directed to one or several inline pickup cells that are backfilled with a dilute gas of atoms or molecules, mainly molecules in our case. And these molecules can now be picked up by the droplet, for instance, this iodine molecule. And as it is being picked up, it cools to the temperature of the host of the helium droplet, and it acquires this low temperature. And then we send the doped helium droplets into our reaction chamber, where they can meet the lasers. So let me show you what happens if you do adiabatic alignment. Well, maybe I should just show you. So this is, of course, a schematic. This is what it looks like in reality. This is an image, so this is a picture of one of our machines. The helium droplet beam runs here, and the gas phase beam runs here, and then the interaction, the reaction chamber is here, and all the lasers are on the other side. So this is a home-built instrument, and it actually works very well. So I want to try to convince you why on earth should you ever put molecules into helium droplets. Isn't this kind of just making life complicated when you have access to these beautiful gas phase molecules? Well, it turns out there are quite some interesting stuff. So this is the first example I'll use to try to convince you why this is interesting. So helium droplets are cool. What do I mean by this? Well, this is something I could have shown you before. This is the degree of alignment measured as a function of time. And this is a view graph you already saw in the case of isolated molecules. So you saw how we could measure the degree of alignment as a function of time. So what we do now is we make a series of these measurements, but stay at the peak of the pulse. And then we measure the degree of alignment as a function of the intensity of the laser pulse. And you can see here it was about 0.9 terawatts per centimeter square. So this is how these curves come about. Degree of alignment, best alignment you can get for a given pulse as a function of its intensity. Now, if you look at the blue curve, this is the result for gas phase. And the best alignment you can get is about 0.9 at the highest intensity of the pulse. But if you do the same experiment for the molecules embedded, so iodine molecules, embedded helium droplets, you can see that it simply performs better. So droplets beat gas phase, and the reason that it does so is that the droplets are cool, and well, I should be more precise, they're cold. So they are 0.38 Kelvin compared to 1 or 2 Kelvin on the gas phase. And this is making a difference when you want to create strong alignment. So we reach 0.96, we could go a bit higher. And this is not just for iodine molecule, this is for many other molecules. There are other advantages. So when you do applications of aligned molecules, you like them to be field-free, because the alignment field can perturb applications, in particular if you involve electronically excited state. An alignment field is poison for electronically excited states because it leads to destruction of that state. So one way to do this is that if you have the alignment pulse, you can actually truncate it. So this is again the alignment pulse that you've seen a number of times, 160 picosecond long. It's fairly easy to cut it off like this, at least in PowerPoint. But in practice, it turns out it's almost as easy. And you can ask me how we do this if you like. For now, I'll just show you the resulting pulse profile. This is the gray shape here that's now being truncated. And this is, again, degree of alignment versus time. And if you look at the black curve, and maybe it's nicer to zoom a little bit on the dynamics here around the cutoff, then you can see the black curve representing the gas phase molecule drops like a stone to the floor after truncation. And it does so because once you cut the field, there's nothing that prevents the molecule from rotating, and they will do so in the gas phase. But now when you do the same experiment inside the droplets, this is the, I'm not quite sure the color because I'm colorblind, it's probably purple, but I'm not sure. But let's say it's purple, you can see that it lingers. It doesn't drop off as quickly. And in fact, if you correct for, well, this extra curve here, which I think is blue, is the true degree of alignment. You have to correct your data a little bit because when ions move out of drop, they scatter on the helium. So you have to compensate for this, and we know how to do this. So if you look at this shaded area, there's actually a window of about, I don't know, 7-8 picoseconds where the degree of alignment of the molecules in the droplet stays above 0.83. So 6 or 7 picoseconds, that's enough time to look, for instance, at chemical reaction dynamics. And this becomes even nicer if you go to larger molecules. So this was iodine. This is diiodo biphenyl, where the iodines are placed in each end. You can call that super iodine if you like. So, but just again, look at the contrast between the gas phase represented by the black and the helium solvated molecules represented by the purple, the blue curves. Now there's a window of 15 picoseconds where you have very strong alignment of the molecules inside the droplet. So enough time to do applications. Now I'll show you an application where we make use of these aligned molecules. Now this is not restricted to, I mean, this can be applied to many molecules. This is terthiophene, sort of an example, a small example of a polymer, and this is bromo indigo. So this is sort of a bromo. It's tetra bromo indigo. This is a cousin, if you like, a chemical cousin to the dye that you use for making blue jeans. And in both cases, you see much the same behavior. I don't have the gas phase here because actually these molecules cannot easily be run in gas phase. There's another advantage of using helium drops that you can pick up molecules that are normally destroyed if you try to get them into gas phase, and you can cool them, and in this case, free alignment. So what are these strongly aligned molecules good for? Well, one thing you can do is you can image molecular complexes. And this is as an example of a small system where we aligned carbon disulfide, not the molecule, but the dimer. And the dimer, so this is a system consisting of 2 CS2 molecules. And what we do now is we strongly align them, and now we take images, for instance, of the parent ions. So this would be molecular ions, CS2 plus ions, but also fragment ions. And I'm not going to go into the details how we analyze these, but combining these two recall ions with the fact that we know how the dimer is oriented in space, aligned in space, we are actually able to reconstruct the structure of this dimer, which happens to be a cross-shaped. So you're entering the regime where you can determine structure of dimers, which is important as a precursor for chemical reactions.
Sorry, Professor Stapelfeldt.
Yes, go ahead.
We have 1 minute left.
That's plenty.
Okay, thank you.
So you can also do this with more complex systems. Well, this is OCS, but if you look at something like dimers of large polyaromatic hydrocarbons, you can actually also go in and determine the structure. And this is quite important because these dimers are conceived as being useful for organic solar cells. You can also go in the other regime and study the rotation dynamics of molecules in the presence of this helium droplet. And this is a dissipative environment where you can look at the coupling between angular momentum that's initially deposited in the molecule and how it flows out into the surrounding superfluid environment. So this is quite interesting and something we're studying actively. You can do unusual alignment because not only can you put molecules into the center, but some molecules like the dimers of alkali atoms reside on the surface because they're heliophobic. They don't like to come into the droplet. And now you can all of a sudden study molecules living in a two-dimensional world. And this turns out to be a lot of fun. So I will end by saying that what we are really interested in, and I think where helium droplets has an amazing potential, is the fact that you can make complexes of a variety of molecules. And this means that you can actually study time resolved, or you can study chemical reactions as a function of time by initiating reactions, for instance, electron transfer, like is illustrated here, or you can imagine reactions, complexation of molecules, time resolved solvation dynamics. So this is actually what we're doing, and we have now the first result where you can do these kind of things. So this is where the droplets are. This is not an easy experimental technique, but the potential is enormous. So I'm extremely happy we do this. And the ability to align or orient molecule means that you can get the best of and the most informative view of the molecules that you study. I'm very sorry for all these technical things, but thanks a lot for being patient and listening to me. And I would like to acknowledge the wonderful team and the sponsors, ESC, that's over. My main sponsors now is the Willem Foundation. This is, some of you may know, this is Velux Windows. This is Rooftop Windows, and they support our research very generously. Thank you very much.
Thank you, Professor Stapelfeldt, for this nice talk. And we are open now for questions. If you have any question, please type it in the chat or raise your hand by going in the bottom of the screen. There is an icon called the reaction. From there, you can raise your hand and we can open your mic to ask questions. In the meantime, I have a question myself, actually. On the first part of your talk, when you were talking about, let's say, non-adiabatic alignment, you used as examples always some kind of, let's call it simple linear rotor molecules. Is there, in your opinion, some limitation on the complexity of the molecules that can be aligned? Because if we go to maybe more complex asymmetric rotor molecules, I think that this is going to be more complex.
Yes, thank you for the question. So yes, there are limitations. You can call them limitations or you can call them opportunities. So if you go to large molecules, so normally if you take a small molecule, like CO2, then what the laser pulse will do is it will interact solely with the rotations. But if you go to larger molecules, then the vibrations will start to be low frequency vibrations or low energy vibrations. And the laser pulse will also be able to, the alignment pulse will be able to create superposition of vibration states. In fact, and I'm sorry I spent so little time on this, but this molecule, biphenyl, and this motion here is in fact an example where you, with a laser pulse, induces a superposition, not of rotation states, but of vibration states, or torsion state, if you like. It's still a normal vibration. And now you can study the dynamics of vibrations. So this is, you can consider this as a limitation that at some point you will start to mix vibrations and rotations. But I like to see this as an opportunity for learning about intramolecular dynamics. That there are limitations, of course, if you deal with molecules that are that are very round, some chiral molecules, then it's not so easy to align them because the polarizability tensor is almost isotropic. So a linear molecule, of course, I mean, has a wonderful anisotropy, so the polarizability is large along the bond compared to perpendicular to the bond. So most molecules actually are polarizability anisotropic, so they can be aligned. Sure, some better than others, but in general you can align. I saw there was a question, and I think the question was that how do you manage to cut the field in time in the nanodroplet experiment? So the laser pulse we use for aligning molecules in the adiabatic regime is the laser pulse that in a way comes out of an amplified titanium sapphire laser. So you know, when you do amplification of short laser pulses, you stretch the pulses and then you amplify, chirp pulse amplification. This is what the Nobel Prize was given for a couple of years back. When you have this chirp pulse, then the frequencies are coming out spread in time. So you can almost say time and frequency are the same. All we do is we put in a long pass filter that cuts all the, or is it short pass? I can't remember, but we come in a filter. We put in a filter in the laser beam that cuts half of the spectrum, and that spectrum is the part of the pulse that comes late. So it's cut. So it costs 150 euros from Thorlabs, so it's a cheap one. You can do this better if you do a pulse shaper. Then you can probably make a slightly faster cutoff, but it works fine for us.
That's a clever solution, actually.
There is a question from Fernando. He says, how many GAs participate in the rotation wave packet generated molecule embedded in a helium droplet in comparison with the case of the isolated molecule? That's an excellent question, and it's an interesting one because so in general the rotation constant when you put molecules into helium droplets becomes larger, because here's a molecule, if you can see my camera. So a molecule is actually solvated by helium because for most molecules there's a positive attraction of helium to the molecule. So the helium will form a solvation layer around the molecule, and as the molecule rotates, it co-rotates with this shell of helium atoms. So moment of inertia becomes larger, and thus the rotation constant is smaller. So in general, there will probably be more rotation states. However, it's also different because the rotation structure is quite different for molecules in helium droplets, because the centrifugal distortion constant is much larger, which you in a very simple picture can think about as the molecule rotates with the helium. This helium, it's easily displaced, so then you can stretch the bonds even more and increase the moment of inertia further. So it's not the same. So in direct response to Fernando's question, I think I can say more states in general.
Okay, thank you.
But it's a very interesting topic by itself. Thanks a lot.
Thank you for answering also the questions. Unfortunately, we don't have any more time, so I encourage all the participants, if you have other questions to Professor Stapelfeldt, you can contact him directly. And thank you for your nice talk again. And
sorry for the problems.
Don't worry, it happens with online events. So we can go on with the next talk, which is a talk by Dr. Sonia Marggi. From January, she is an assistant professor at the Universidad Complutense de Madrid, after being a postdoctoral fellow, holding an individual Marie Curie fellowship in the group of Professor Steve Leone at Berkeley. And she will today present some results obtained during her postdoc. So, Sonia, the stage is yours.
Okay, do you hear me? And you see my screen? Everything?
Yes, everything is perfect.
Okay. So as Gabriele was saying, I will be presenting some results on molecular dynamics probed by ultrafast transient spectroscopy, get at the Leone group at Berkeley. So we are interested in the photoinduced dynamics in polyatomic molecule in the gas phase, so where we use this kind of pump probe schemes, where first laser induce the dynamics that can be governed by curve crossing at conical intersection, and the second laser pulse probes it. So the recent development of ultrafast light sources from the Attosecond to few-femtosecond has opened new avenues to disentangle and visualize in real time the couplet electronic and nuclear dynamics that happen at this conical intersection. The downside of it is the reduced spectral resolution that we get sometimes, since the pulses get narrow temporally, they get broadened spectrally. So one way to avoid this, partially avoid this, is to use a XUV transient absorption spectroscopy. So we use core to valence transition induced by an XUV pulse to probe the dynamics. So the pump laser induces the dynamics on the valence shell, and then the core to valence transition is used to probe the dynamics. So this kind of transition are really highly sensitive to the electronic configuration, and they are an excellent probe of the nuclear and electronic dynamic going on in the molecule. So in addition to that, at each time delay, we will record the complete XUV spectra, and we will use a broadband XUV pulse. In that way, we avoid the spectral resolution limitation by the probe pulse spectrum. So we only have the spectral resolution by the pump pulse. So this technique was successfully used a couple of years ago in a diatomic molecule in IBR, where a visible pump excites the molecule, and the transient spectra allows us to observe the dynamics going through a curve crossing, and the adiabatic and diabatic pathways were clearly resolved on the experiment. So the idea now is to use this technique on larger systems and on other kinds of dynamics. In particular, I will present results on two different systems. First, how we can visualize vibrational motion on molecular iodine, and then about some photodissociation dynamics in alkyl iodides. So first, regarding the iodine, it's like a really benchmark molecule since the first ZY experiments. So if we use a visible pump pulse, we will populate this B state, and we can create a vibrational wave packet that will oscillate on this B state. So the idea is to observe it through the XUV transient absorption spectroscopy. So this coherent motion was already reported in two different diffraction experiments, one using femtosecond X-ray diffraction and one using this mega electron volt ultrafast electron diffraction experiments. So both of them were done at SLAC in Stanford, and they both observed like a couple of iterations of the wave packet from the inner to the outer turning point. So we want first to see if we can observe this with the transient absorption. So we use this, as I was saying, a visible pump pulse will produce a broad vibrational wave packet of the B state, and the dynamics is probed through core to valence transition that correlate with this well-known atomic transition of the iodine. So we can also identify the atomic iodine in the ground spin orbit state, or the excited one. So these transient absorption experiments are complemented by calculations using this code, the SOGMCQDP code that was developed by Dowsing. So it allows us to compute potential energy curve for both the valence and the core excited state, and to simulate the wave packet dynamics on the different excited state considered by solving the nuclear TDC. So before presenting the results, I will briefly comment on the experimental setup. So we use a CEP stable titan sapphire laser delivering like 1.8 millijoule, 27 femtosecond at around 900 nanometers. And the output of the laser goes into a hollow core fiber filled with neon, so for spectral broadening, and we use some chirp mirror for post-compression. In that way, we obtain like 3.7 femtosecond pulses, like a broadband from around 500 nanometers up to 1000 nanometers. This pulse is separated in two arms. The first one is used to produce the pump. So we use a couple of dichroic mirrors to separate the visible part. So it goes roughly from 500 to 650 nanometers. So it will allow us to populate a large number of vibrational level on the B state. And then it's characterized by this cross correlation in helium around 13 femtosecond. The other part is used to produce isolated attosecond pulses in an argon gas phase through amplitude gating. So we obtain this kind of of a broadband XUV pulses that were characterized by a streaking experiment around less than 200 attoseconds. So for the two pulses interact later with the sample that it's on a gas set, in that case the iodine, and then the XUV spectrum, it's measured using an XUV grating on camera. So if we consider that we have no gas in the gas set, we will obtain this kind of spectrum. And once there is a gas, there is like some kind of absorption and this kind of structures that correspond to this balance to core transition. So what we do for each time delay, we will measure this spectrum and we will subtract the contribution from the XUV pulse alone, so that we only have the structure corresponding to the dynamics induced by the pump pulse. So here are the results for the iodine molecule. The transient spectra are plotted as a function of the XUV photon energy and as a function of the time delay between the pump pulse and the XUV probe pulse. So the intensity in colors reflects delta OD, so a variation in the optical density. And as we observe, we have here some depletion with some oscillation that can be assigned to the ground state depletion. And since we are using a low field pump pulse, this kind of depletion are explained through these resonant impulsive stimulated Raman scattering features, where there is like a pump and a dump producing some vibrational coherences. Then we also observed dissociation of iodine reflected by the production of these iodine start and iodine in its ground spin orbit state. And then we have like some features here giving rise to some oscillations. So all these features were perfectly reproduced by the simulated maps, and I will only focus for this talk on the oscillations that are observed here, so on the wave packet oscillating. So if we do a zoom, we see here the results, and we see like we have this kind of shifting features that appears here. And actually, if we imagine or brought a vibrational wave packet that it's oscillating on the B state, these shifting features represents the XUV curve that has like a repulsive potential. So the wave packet is going through this. So if we compare with the simulated dynamics on the B state only, we see like we have the same kind of features that are reproduced. So just to comment, we see like we have some difference in intensity. For instance, here we see very well how the wave packet from 0 to 200 femtosecond, the wave packet goes from the inner to the outer turning point. And once it gets to the outer turning point, we don't see any intensity on the experiment, and it almost disappears on the theory. That's due to the dispersion of the wave packet. If we look here to the result of the simulation as a function of the internuclear distance and the time delay, we see how the wave packet it gets really dispersed around the outer turning point, and then gets some recompression again when it gets back to the inner turning point, and so on. So that it's well reflected also on the experiments by the difference in intensity between this part here and this point here and this part. So now, beside this, we can also get some information in the core excited state on the potential energy curve, since we are probing them. So we can take the position of this feature as a function of the time delay, and we will have this kind, so that corresponds to the experimental results. And if we compare this with the classical dynamics, one dimension, we can get for each XUV photon energy at each time delay, we can associate an internuclear distance, and we are getting direct information on the core excited potential energy curve. And what we are obtaining indeed is directly the core to valence transition energy as a function of the internuclear distance. So that's the results on the iodine. And then now the second goal was to go for bigger molecules. So starting with the alkyl iodides. So for that, we needed a UV excitation. So the visible and the near infrared pump, they usually lead to strong field ionization and to multiphoton non-resonant processes, which are usually difficult to disentangle because we have a lot of features that are overlapped. So a UV allows us to do a one photon excitation, and we were in particular wanted to look at couplet electronic and nuclear dynamics at conical intersections. So why the alkyl iodides? Well, it's like a benchmark, a family of benchmark molecules now. So they are characterized by a first absorption band between 230 and 300 nanometers, where 3 excited states can be populated, the 3Q1, 3Q0, and 1Q1. So in particular, in general, the 3Q0 is the one that absorbs the most. And then the dissociation is controlled by a conical intersection between the 3Q0 and the 1Q1, leading to some branching ratio between the two spin orbit state of the iodine, the ground and the excited web. So the further idea besides alkyl iodide was to try to look into this allyl iodide, where we have a double bond, and see how it modifies the dynamics, and in particular if we can get this resonance stabilization, where the radical here gets to this. So first we developed the UV setup was developed by Christina Chang during her PhD. So the idea is to get UV pulses pretty short temporarily, so we can see the dynamics. For that, we combine the second harmonic generation, or generated the 400 nanometers from the output of the laser by its second harmonic generation BBO. These 400 nanometers are mixed with the output of the hollow core fiber, so with the broadband NIR, and we obtain the UV pulses on a BBO. And this allows us some tunability of the UV between 260 and 280 nanometers, and we obtain UV pulses around 20 femtosecond, as reflected by the cross correlation in xenon. So the rest of the experiments is the same. We will measure the XUV spectrum for each time delay between the UV and the XUV. So the first molecule we chose was the methyl iodide, which is like the most prototype molecule and the most simple alkyl iodide. So we see again at higher XUV photon energy, we see this kind of oscillation and depletion of the ground state. But if we focus here on the region where we see the dissociation, you can see all the dynamics. So if we zoom in, we see different features, and we can in particular map all the dissociation from the photoexcitation to the dissociation into iodine and iodine star. And we can assign the different features, in particular based on calculation done by Han Wang and David Prendergast at the LBNL, and where we can assign the feature here to the initial population of 3Q0, and we can see how it gets through the conical intersection. Particularly, if we zoom in this region here, we can see how the wave packet bifurcates at the conical intersection in well agreement with the theory. So we really map the dynamic for the conical intersection, getting a time for the bifurcation around 15 femtosecond. So now we went to the allyl iodide, the bigger molecules. So the analysis is quite preliminary, but we obtained the same kind of similar features. If we assign them based on the Han Wang calculation of methyl iodide, we could assign this to a similar dynamics on the 3Q0 and 1Q1. And we observe the same kind here of bifurcation. And actually we get bifurcation of the conical intersection that it's delayed to 23 femtosecond. But as I was saying, all these analyses are pretty preliminary and calculations are in progress by Jesus. So to conclude, we have shown how transient absorption spectroscopy can be used to visualize coherent vibrational motion in I2, where we can see the wave packet and we can obtain information on the core excited potential energy curves. And on a second topic, we have shown how we can use this technique to directly visualize the dynamics and the dissociation of alkyl iodides and the bifurcation of a wave packet at the conical intersection. So I would like to thank all the members of the Lione group, in particular my co-workers, so Christina Chang, that was working in the lab with me, Yuki Kobayashi, who was doing his PhD before me and was doing the calculation on the iodine, and Steve Lione. Thank you all for your attention.
Thank you, Sonia, for your nice presentation and nice experimental results. So we are open for questions, if anyone has some of them. In the meantime, I have a general question, let's say, which is about, okay, so you are looking at conical intersections, which are, of course, very interesting, let's say, feature of many molecules, also, for example, biological molecules. And these are looked also, for example, with the UV IR or UV visible spectroscopy, which is the, let's say, the main advantage of going with an XUV probe instead of using an IR visible one that is coupling just the two states involved in the conical intersection.
Okay, for this kind of transient absorption spectroscopy, you probe the dynamics through this core to valence transition. So you need an XUV. If you want to do that, you need at least an XUV probe, since all these transitions are at high energy. So you need at least an XUV or even an X-ray if you want to probe, like for instance, the carbon KH. So they allow like a higher sensitivity because you can follow this transition in energy, and so you will see how the wave packet is moving. When you use an IR to probe, you have like multi-photon processes and non-resonant processes. So the data gets blurry, let's say.
Okay. Everything fine. Okay.
That was my window.
We have a question from Lorenzo Colaizzi that is asking, in the CH3I experiment, what is the effect of the duration of the UV pump on the bifurcation time you measure?
Yeah, so it's true. Like, yeah, it's true. Like we have actually a 20 femtosecond pump pulse duration, but we get to see the dynamics closer to that. So it's like taken into account when we do in the error bar, these 4 femtosecond. Well, I can share my screen again, but yeah. So this error bar takes into account the pulse duration. So even though we have like a cross correlation around 20 femtosecond, we can pretty well see the bifurcation, even though. But yeah, it's complicated. Yeah. So I guess there is always a compromise between the pulse duration and the spectral broadening you want. So as you get a shortage of 20 femtosecond, you will get a broader spectrally. So you will lose also resolution from that. So.
And I saw also that in your slides where you have the XUV, let's say, spectrum, it is cut to 70 electron volt, if I don't remember well. Yeah. Do you have also, I mean, have you tried also to perform some experiments towards more, let's say, the soft X with transient absorption? Or you just... So
there's, that requires a different setup. So we can go up to 120 EVs with our setup. I mean, using 800 nanometers as a pulse to produce the attosecond pulses. If we want to go to the X-ray, we need to use like an NIR pulse to produce the attosecond. So there is another lab, a new lab that in the Lione group that it's getting that, yeah, but not mine.
Okay.
It was a different laser. Yeah. You need a different setup.
Okay, I see. So if there are no more questions, I think we can go on with our schedule. So thank you again, Sonia, for your nice talk.
Thank you again. Thank you very much.
And the next speaker is Ms. Alexie Boyer from the Institut Lumière Matière in Lyon. And she's a PhD candidate in the group of Professor Le Pen. And her research focuses on XUV-induced molecular dynamics. And so, Alexie, the stage is yours.
Thank you for the introduction. So hello, everyone. First, I would like to thank the organizer for giving me the opportunity to present my work today. So my name is Alexie Boyer, and I'm starting my last year of PhD at the Institut Lumière Matière in Lyon. And today I'm going to present some results about ultrafast dynamics induced by XUV in molecular spatial. So over the past 20 years, the development of Attosecond technologies have brought new tools to study in real-time electron and nuclear motion. And among other, it gives the possibility to study XUV-induced dynamic and in particular, dynamics induced by the photoionization. And up to now, the experiments have been mostly performed on atoms and small molecules, and are still carried on with increasing complexity of the techniques in order to describe more and more precisely those dynamics, so in small systems. And this experiment have also been developed in order to study more complex systems, polyatomic molecules, with the aim of understanding the effect of having a lot of electrons involved in the dynamics or a lot of number of degrees of freedoms. And already remarkable results have been obtained about charge dynamics, electronic and vibrational coherence, and more globally about energy dynamics. And the question that I would like to address here is how could electron correlation possibly impact the dynamics of photoionized molecules? So to understand that, we need to take a closer look at what's happening during the photoionization of a molecule. So when a molecule is ionized, an electron is ejected and a cation is created. And the electronic state of this cation can actually be predicted by theories such as ADC calculation, represented here, where you can see the probability to create a state depending on its energy. And if we look more into the details of the calculation, what we can see is that at low energies, the states can simply be described as monoelectronic states, meaning that when we eject an electron, a hole is left in the electronic structure. But if we start to look at higher energies, then to describe the states, we need to consider them as a superposition of electronic configuration, for example, one hole configuration, but also two hole, one particle configuration, and so on. And if we go even higher in energy and we start to be closer to the second ionization potential, then this multi-electronic states become so close in energy that they start to look like a band. So those bands are called correlation bands that have been predicted by theory almost 40 years ago by Söderblom, and are thought to be a universal feature of all large photoionized molecules, so at high energy. So the role of electron correlation here is actually to create those bands. So our goal in Lyon was to understand how those correlation bands could possibly impact the dynamics. So to do so, we performed a time-resolved experiment on polycyclic aromatic hydrocarbon, PAH, molecules that are easy to scale by increasing the size. And so here you have the XUV area pump probe experiment that we used. So it consists of a Mach-Zehnder interferometer, so where the first arm is used to generate the XUV pulses to high harmonic generation. Then we have several optics to isolate those pulses. And the second arm is delayed compared to the first one in order to probe the dynamics induced by the XUV. And at the end, both beams are recombined at the interaction region with the neutral molecules in gas phase. The product of this interaction is then detected using time-of-flight spectroscopy. So at the end, we have a mass spectrum for each pump probe delay. And in order to study the dynamics of the correlation bands, we decided to look at the variation of the decatanian yield as a function of the pump probe delay. So what's happening during the experiment? So the neutral molecules is going to absorb an XUV pulse of few tens of eV, so well behind its ionization potential. And in that case, as we saw just previously, the created cation will be left in a large number of configurations, and the correlation bands will appear just below the second ionization potential. So in that case, the absorption of infrared will lead to a second ionization step, leading to an increase of the decation yield at the zero delay. After some time, the correlation bands will relax and we'll have a decrease of the decation. So at the end, we have a quite simple time-dependent signal that can be fitted with just one exponential decay from which we can extract one time constant. And since we are looking at the decation with an higher pulse, we are limited to the dynamics of highly excited electronic states, so lying just below the second ionization potential, meaning that this time constant corresponds to the relaxation of the correlation bands. And here I only show you the detail for the coronan, but we performed the same experiment for different molecules with different area and XUV condition represented by a different color here. And we saw that our results do not depend on those parameters. And so if we now look at all the experimental results that we obtained, you can see that it shows a very simple trend with a nonlinear increase of the relaxation timescale of the correlation bands, depending on the number of valence electrons, so the size of the molecule. And so to understand how the relaxation occurs inside the correlation bands, we try to develop a model based on an analogy with solid state physics. So if we go back to the calculations that I was showing to you at the beginning, it was performed on Ultrafast by our colleagues from the University of Heidelberg. And if we look at the corresponding density of states, you can see that it linearly increases at the energy range of the correlation bands. And regarding this high density of states, we developed a model that compares those bands to bands in solid. And in that case, we assume that the relaxation inside the correlation bands can be described as electron phonon scattering, just like in solid. Assuming that, and starting from the Fermi-Golden rule, plus taking into account the linearity of the density of states, we were able to derive a very simple relation between the relaxation timescale of the correlation bands and the number of valence electrons. And as you can see, this simple relation only depends on two parameters. So τ0, it's the mean lifetime of an electron inside the correlation bands, and NCB, the minimum value from which our model is valued and is related to the strength of electron correlation. So those two parameters, we were able to derive them from ab initio calculation in the specific case of naphthalene, the smallest PAH that we studied. And if we go back to our experimental results, and if we try to plot this law using the parameter extracted only for this molecule here, naphthalene, we obtain the orange curve that you can see here. And as you can see, it seems to perfectly fit all the experimental data, not only naphthalene, but all the other PAH, meaning that the two parameters seems to be common to whole class of molecules, so here PAH. In order to extract more precisely these two parameters, we performed the fitting over all the experimental points, and we obtained these two parameters here, so for PAH. In order to confirm our model, we also performed experiments on another class of molecules, diamondoids, so using the same procedure. And here you can see the experimental point together with the fitting curves, and it seems to show that our model seems to be general to different class of molecule, and we just need to extract new set of parameters depending on the class of the molecule. So of course, the relaxation of the correlation bands is only the first step of relaxation. And we can ask ourselves, what are the other relaxation pathways following the photoionization of the molecule? So up to now, I only talk about the decation yield, depending on the pump-up delay. So by looking at the decation, we are limited to highly excited electronic state just below the second ionization potential. But now, if we change our observable, and if we look at the fragmentation as a function of the pump-up delay, then we don't have this energetic barrier anymore. So we will see more processes. And that's indeed what we saw in the fragmentation. So here you have an example in a fragment of anthracene, where you can see two dynamics. A first one, a decay one, and it's actually exactly the same time scale than in the decation. So it's also allowed to probe the dynamics of the relaxation of the correlation bands. But we also see another dynamics, a population one, represented here in green. And we associate this dynamics to vibrational dynamics. Indeed, just after the photoionization, and actually even after the relaxation of the correlation bands, only specific vibrational modes are populated. There is no statistical distribution of the vibrational energy yet. It will take some time before the vibrational energy will distribute along all the vibrational modes of the molecules. So we associate this time scale to the time scale of this redistribution of energy, and it actually corresponds to the first step before a complete IVR process. So here I only show you the detail of anthracene, but this population dynamics is also observed in other PAH. So you have the experimental results in green here. And it has also been observed in naphthalene by the group of Oleg Kornilov quite recently. So to conclude, so if you remember, my question was how could electron correlation possibly impact the dynamics? And actually we saw that this dynamic seems to be driven by the relaxation of correlation bands, so features created by electron correlations. And we were able to understand this relaxation as electron photon scattering, just like in solid. I also briefly mentioned another relaxation pathway, the vibrational dynamics. And this vibrational dynamics seems also to be general to several classes of molecules, since we also observe it in some diamandoids. So here with adamantane and diamantane, with timescale of few tenths of femtosecond. And just before finishing, I would like to mention other projects that we are working on. So today I only talk about dynamics following the photoionization, but another part of my PhD consists of looking at the photoionization itself. So by measuring attosecond delays, and in particular, looking at the effect of the molecular structure on these delays. So experiments that are still performed on, let's say, model molecules, so carbon structure, but we are also trying to push further all those experiments on more complex systems, and especially on fragile molecular ions. And very recently, we showed that by controlling the microenvironment of a peptide, so by changing the adduct atom here, we are able to tune the timescale of the charge transfer induced by UV, going from few hundred of femtosecond up to a few picosecond. And going back to XUV, all the experiments that I showed you today, we are actually now able to do them, perform them on large fragile molecular ions. And we already have some very promising results. So here you have an example of ultrafast dynamics induced by XUV of few tenths of femtosecond, obtained in protonated reserpine represented here. So now we have the ability to look at dynamics induced by XUV not only in model neutral molecules, but also to this kind of molecular ion, and even going up to proteins. And we really think that it will open a lot of opportunities and new experiments to perform with very new interesting physics behind it. And we are really excited about that. And actually, if you are also interested in this kind of experiment, we are open for collaboration, so feel free to contact us. And with that, I would like to thank all the people who worked on this project, so people from our group in Lyon, but also other collaborators who work on the question of PAH, and in particular, Victor Després and Alexander Kulev, who did all the calculations that I showed you today. And thank you for your attention, and if you have any question, feel free to ask. Thank you.
Thank you, Alexie, for showing this very interesting work that you did. If there are any questions, we're open for questions. I encourage you to raise your hand in order to being able, let's say, to ask your question directly if you want. And in the meanwhile, I have just one question on the first part of your talk, so regarding the universal behavior in correlation bands. In your conclusion, you said that you are also starting investigating more, let's say, complex molecules in the sense that are not just carbon-based molecules. And have you checked also if this universal behavior is present also in molecules that are not just carbon-based, but maybe have some other atoms or are more complex?
So actually, so the experiments that we performed here, so are indeed only on carbon molecules, but we also compare those results to results presented in literature, for example, phenylalanine or caffeine. And actually, it seems to fit quite well our curves, especially for caffeine. The phenylalanine seems to be a little bit off. I think it's maybe a little bit lower, but we think this is maybe related to the fact that it corresponds to maybe another class of molecules, because it's not just planar molecules. Phenylalanine is more kind of 3D, so it's more complex. So maybe it's just So it seems to fit quite well, but maybe it's another class of molecules. So there's still a question about how to define exactly those classes, because it's related to the geometry of the molecules, but it seems to perfectly fit also other data. For example, caffeine, I think it's perfectly on this curve for the pH, because it's actually very similar to a pH.
So since caffeine is fitting this curve, you think that this behavior is much more influenced, let's say, on the geometry of the molecule with respect to the, let's say, atomic properties of the chain, right?
Yeah, actually,
okay.
So the two parameters that are, so this one depends a lot of the coupling between the states. So it's probably related strongly to the geometry of the molecules, because it depends on the vibrational modes involved in the relaxation and also.
I see, thank you. So I don't know if there are other questions from the audience. Okay, seems like we have no more questions. So thank you again, Alexie, for joining us and to show us these very nice results. And now we will have a small coffee break of 20 minutes in order to, let's say, restore a little bit before the second part of the session. So thank you again for joining this first part of the session, and grab your coffee and see you in 20 minutes. So let's go on with the session, and the next speaker is Mr. Lorenzo Colaizzi. He is a PhD candidate from DESY Hamburg in a group of Professor Francesca Calegari, and today he will talk about the ultrafast molecular dynamics induced by few-femtosecond ultraviolet excitation. So Lorenzo, the stage is yours.
Okay, which screen are you seeing?
Now we are seeing in the presenter mode. So
okay,
with the
this. No, it's fine.
Now it's perfect. Okay, thank you.
Do you hear me well? It's fine. The audio.
Yes.
Okay.
Both the audio and video.
Okay, perfect. So thanks. I'm Lorenzo Colaizzi. I'm a PhD student in the Attosecond Science Group in Hamburg. And first of all, I would like to thank the organizer for giving the opportunity to present our recent results in ultrafast molecular dynamics induced by few-femtosecond UV pulses. UV radiation, as we all know, is the most energetic part of the electromagnetic spectrum which reaches the Earth. This is due to the ozone layer, which acts as a shield and stops the most energetic part and lets it pass the UVB and UVA spectral region. And although the UVB is just a small percentage of the total energy, this is very fundamental for many biological and chemical processes, such as, for example, vitamin D production, which is in our body is regulated by absorption of UV radiation. UV radiation can also be dangerous for processes such as the DNA damage in the form of dimerization of the nucleobases. But all these phenomena are known to be very fast, and this is on the order of hundreds of femtoseconds, or even below. And this is why in ultrafast spectroscopy, their investigation has always been limited by the availability of ultra short UV pulses, available. For example, today Sonia presented a very nice experiment in which they use a 20 femtosecond pulse, and they combine this with the XUV attosecond pulses in order to increase the time resolution and be able to observe very fast dynamics. Another reason of going down with the duration of the UV pulse is also the investigation on another class of very fast phenomena, such as charge migration, which happens in the order of attosecond or few-femtosecond time scale, which so far have been studied only in the cationic states by using XUV attosecond pulses. And one question that could arise is that if we use enough short UV pulse, can we trigger also charge migration in the neutral molecule? So in our lab, we've been pushing the duration of the UV pulse by exploiting third harmonic generation in noble gas, because normal generation scheme based on crystals cannot be applied due to the intrinsic second order dispersion they introduce. Therefore, we rely on dispersion-free mediums such as noble gases, which gives the advantage of producing short pulse, but at the expense of low conversion efficiency. So in our setup, we have to rely on high pressure glass cell, which is a micro machine glass cell, which confine the gas in a very small region, as you can see here. Maybe I should put the pointer as well. You can see here, and was designed in collaboration with the group of Roberto Sellame in Milano. A typical spectrum we can obtain, for example, in 6 baron neon, is the shape, and has a transfer limit duration of 3 femtosecond. The generation setup for the third harmonic is integrated in Attosecond beamline. So you can see here 3 arms on the beamline in which we can either generate harmonics in this arm, or as we discuss, as we will be for all the results we discussed today, we can just switch off the generation and use the near infrared pulse, the few cycle pulse, to probe the molecule. For example, we use this to characterize the UV pulse, because all optical techniques are still not usable because of the dispersion they introduce. And therefore, in order to characterize these ultra short pulses, we rely on IR cross correlation in xenon, and we were measuring the xenon plus yield, so the photoionization of xenon, as a function of the delay in between the two pulses. The shape of this curve, especially this step-like function, is due to the fact that with the absorption of 2 UV photon, xenon is excited on a very long-lived metastable state with a nanosecond lifetime, and therefore, which is practically constant on our time scale, and requires also additional 2 IR photon to ionize. And by knowing the number of photons, we can recover the duration of the UV from the full width maximum of this distribution. For example, in 2019, by using a 5.3 femtosecond pulse, we measured the 1.9 femtosecond pulses, which were the shortest UV pulse ever generated. For the experiment I will talk today, we used a bit more complicated detection system in which the laser is interactive with the molecular source coming from the top, and is ionizing. The probe pulse is ionizing the molecules. On one side, we can detect the electron velocity map imaging, so we can detect the angular distribution and the kinetic energy of the photoelectron. And on the other side, we can accelerate the ions and measure their time of flight in order to obtain the mass spectrum. The novelty of this system is that we can detect both the particles simultaneously and single shot in order to exploit methods such as covariance mapping. As a target, we decided to use some very well-known molecule as a benchmark experiment. So we will use methyl iodide and acetone, especially because their absorption cross-section matches quite well the spectrum of our excitation pump. And in particular, methyl iodide, as also Sonia presented today, is a very well-studied system. Because of the very nice dynamics in this dissociation dynamics induced by the presence of this conical intersection after the absorption of 1 UV photon. In particular, this has been measured to be very fast, on the order of 10 or 20 femtosecond. For methyl iodide, I will present only the ion part, because we are still working on the electrons. And in our scheme, we will use 1 UV photon to excite and 3 IR photon to ionize, and we will obtain the parent ion, the iodine, and the methyl group. So the fragmentation will happen on the CI bond. This is the time-dependent signal of the 2 main fragments we obtain, and as you can see, the main feature are that there is an extremely short rise time due to the duration of our cross correlation, which is around 3 femtosecond sigma, and a shared similar ultrafast decays for both the fragments, which could be assigned to the wave packet evolving through the conical intersection, which decrease the number of fragments after, so it increased the ionization energy. But what is even more interesting is that after 30 femtoseconds, so for sure after the conical intersection has been passed, we see an increase, another rise of the iodine signal, which goes back up to the original one. And in principle, the molecule is reactive also after the photodissociation has started. So we don't know, we don't have a clear interpretation of these results. At the moment, we are working with the group of Fernando Martin in Madrid to give a more quantitative explanation of this. For acetone, although the absorption cross-section, one photon is matching quite well our spectrum, in literature it is well known that especially for femtosecond pulses, the two photon transition is much more favorable. And therefore, what we're going to do today is to probe the Rydberg states by absorbing 2 UV photons. In particular, the dissociation path of acetone is passing by the breakage of one of these two bonds, so the creation of one methyl and the acetyl, although the methyl signal is very low. So we're going to discuss only about the parent and the acetyl fragment. This is the time-dependent signature. And as you can see, this can easily be understood if we discuss together with this the energy structure, in which after the absorption of 2 UV photon, we need an additional, from our intensity scaling measurements, an additional IR photon to ionize. So we end up in this minimum of the cationic state. As the molecule evolves around and cross this conical intersection with the bypass state, which is above, the absorption of 1 UV photon leads to a dissociation part of the ground state of the cation, which means that the ion yield will decrease. And this decay we fitted in this data is compatible with the crossing of this conical intersection. Of course, there are many different other fragmentation dynamics which are much slower in respect to the time scale we are investigating here. For acetone, I would like also to show the photoelectron, which is plotted here as the angular integrated velocity map imaging as a function of the time delay. And as you can see, the photoelectron shows a much more richer dynamics in which happens in the molecule. And in particular, I would like to point a couple of specific regions, in particular this one in between 1.6 and 1.8 eV, in which we can see that the decay is modulated by 24 femtosecond oscillation, which could be assigned to vibrational coherence of the CH3 umbrella mode. And if we go even shorter with the time step, so we perform a much finer scan and we go a bit lower in energy, we do see the same oscillation. But on top of this, we also see a 3.2 femtosecond oscillation, which is too fast to be assigned to nuclear dynamic and therefore could be assigned to electron dynamic. As to conclude, I would also like to show you what happened when we combine the two measurements in order to perform covariance, which is nothing else that to map the correlation in between the two data sets. So in this case, X is the electron VMI and Y is the ion flight. So we can correlate particular energy region in the electron map to specific fragments. These are the covariance map we can obtain for the parent and for the acetyl, and one can easily interpret this map by thinking that these are the electrons which are emitted only when one parent is detected simultaneously. So we can see that the parent ion is correlated with the low energy part of this map, while the acetyl covers the full range, and in particular is exclusively covering the part in which we observe the oscillation. So we can most likely assign this oscillation to the acetyl fragments. And this will be very important in the goal of studying much more complex molecules. To conclude, I show that with our few-femtosecond UV pulse, we have been mapping the ultrafast conical intersection in the A band of methyl iodide. A similar conical intersection has been observed also in the Rydberg state of acetone. And at the same time, we've been able to observe coherent vibrational oscillation still in acetone, and also very fast modulation of 3.2 femtosecond in the same molecule. And at the same time, I showed that our setup is able to perform covariance mapping, which can gain lots of more information about the different fragmentation dynamics and the different energy level involved. To conclude, I would like to thank my group, in particular Sergey, with which I performed the experiment, and Krishna, who worked on the covariance analysis, and the rest of my group, and also the group in Madrid, we are currently working for the theory to understand better this experiment. And I would also thank you for your attention.
Thank you, Lorenzo, for presenting this nice work. And we are open for questions now from the audience. In the meantime, I would like to ask you, so just to reconnect, let's say, to the question I did to Sonia also in her previous talk, how much is tunable your UV light UV source? Because
actually not much, in the sense that we need to balance anyway the broadening, because it's actually it's not a purely third harmonic generation process, and therefore we have like very small tunability, but in order to obtain such a short pulse and not incur in additional nonlinear phenomena you don't want, because they can induce dispersion or the higher order dispersion, let's say that we cannot move much from the spectrum in order to obtain such a short pulse. If we relax a bit the duration, we have the possibility to move, but not more than a few tenths of nanometer.
Okay. I see. In terms of energy, how much energy can the glass cell, let's say, sustain and produce?
We usually generate with 300, 400 microjoule. Okay. So, and the yield is very low, as I discussed before. So we generate around 100 nanojoule for UV after the separation. So the one we can use for the experiment, let's say.
Okay, thank you. Then we have also a question from Cattaneo asking if you know the degree of correlation of the 24 femtosecond and the 3 femtosecond modulations, if there is any.
No, because we still haven't analyzed the covariance map by looking at the oscillation. So we will
the results. Yeah.
Yes. These were very recent.
I see. So let's see if there are other questions from the audience. I don't see any, so I think we can go on with the next talk. So thank you again, Lorenzo, for your presentation. And the next speaker is Ms. Li Wang from Stanford PULSE Institute, where she is a PhD student working in the group of James Crayan, Philip Baxbaum, and Agostino Brugnelli. And our talk will be about the role of nuclear electronic coupling in attosecond photoionization of H2. So, Li Wang, thank you for joining us, and the stage is yours.
Thank you. I'm just going to share my screen. Do you see the presenter, or?
Yes, we can see perfectly your slides.
Okay, thank you. Yeah, so I'm Anna. I'm a graduate student at Stanford University. And I'm going to be talking about channel coupling in H2 photoionization. So when we talk about channel coupling in photoionization, I typically like to think about this as what's missing from the asymptotic electronic wave functions that we would get from solving the molecular Hamiltonian. So when we solve the molecular Hamiltonian, there are a few major approximations we make. Typically, electron correlation is treated by some sort of averaging, which can remove attosecond electron correlations. And nuclear motion is treated by the Born-Oppenheimer approximation, which separates the nuclear and electronic timescales. When we do this, we remove a lot of interesting attosecond scale dynamics by truncating the Hamiltonian. And when you try to reintroduce those elements, you get these transient off-diagonal matrix elements, which can be called channel coupling. I'm going to talk about how channel coupling is relevant in photoionization of molecular hydrogen, where you have these light, fast nuclear components, which can lead to breakdown of the Born-Oppenheimer approximation because the nuclear and electronic timescales might be able to match when you, for example, excite a excited vibrational state in H2+ and have it interacting with a near threshold electron as it photoionizes. In this regime, if you get that type of timescale matching, you can see nuclear electronic coupling. So the reason we're interested in this in H2 particularly is because hydrogen is found very commonly in many organic molecules. It's probably important. It's also a diatomic with simple accessible vibrational spectra, which we like experimentally. And we have good reason to believe we'll see nuclear electronic coupling in H2 because of the reasons I described here, and also because it's been observed previously. It was observed in dissociating photoionization of H2 by Cattaneo in 2018. And it's been studied in bound hydrogen, like I'm going to talk about, by a couple of other groups. So what we're picturing here is not dissociating H2 photoionization, but bound transitions of vibrational states of the cation. So for example, if we photoionize to H2+, we excite a lot of vibrational states, and as the electron interacts with the nuclei and the nuclei interact with the electron, they may exchange energy and cause transitions between the vibrational states. So I use photoemission delays to study these types of dynamics. Photoemission delays are a measurement of the electron wave packet phase as it scatters off of a molecular potential. When you photoionize, you can kind of think about this as a scattering event. And when the electron scatters through a molecular potential, it's going to pick up phase. Across the full bandwidth of the electron wave packet you create, all of these collected phases are going to interact to create something similar to a group delay in a light pulse. This phase transition, these phase group delays are a lot more sensitive than cross-section for transient phenomena. So they're a nice probe of attosecond dynamics. The way I measure photoemission delays is using a rabbit measurement, which is the reconstruction of attosecond bursts by interfering two photons. How this works is we ionize with an XUV attosecond pulse train. In the spectral regime, this looks like a harmonic cone, which creates many different ionization pathways. And then these ionization pathways, the adjacent ones are interfered using a weak IR probe to create sidebands that have a contribution from each of the adjacent harmonics. So those sidebands, which show up between the harmonics, oscillate in amplitude as a function of the phase offset between the attosecond pulse train and the probe, the pump probe delay. They oscillate at twice the probe frequency, and the phase offset of that oscillation is the rabbit phase, which tells you about the photoionization phase of the electron wave packet. Since this is a differential measurement, this translates nicely into the idea of a group delay for the electronic wave packet. And for context, 2 pi phase of the of like an 800 nanometer probe, which is what we use, gives you about 1.3 femtoseconds of delay. And we're looking at small fractions of a full rotation. So that comes out to tens and hundreds of attoseconds of delays that we can measure using photoionization delays. So for rabbit, we end up with a vibrationally resolved rabbit spectrum. At every one of those harmonic ionization peaks, we get the full vibrational spectrum of H2+, where you can easily resolve vibrational levels 1 through 5 of the cation. Below here is the rabbit spectrogram that you might typically see from one of these measurements. On the energy axis, you can pick out the different vibrational states, which is summarized above in the black line, which is the delay averaged yield, and the blue line, which is specifically the 2 omega oscillatory component that we want to look at. That 2 omega component comes out of the XUV IR delay, which is shown on the y-axis. This bottom plot is actually a mean subtracted different spectrograms. So you can see the oscillations between plus and minus the mean. And you can see a combination of 2 omega oscillations, which we're interested in, and a background 1 omega signal that can be easily filtered out. When we filter out the interesting component, the 2 omega, you can see very nice vibrational peaks, and that demonstrates that we can pretty nicely pick out individual phase values for each one. So once we have those phases, how do we actually use those to learn about attosecond dynamics in the molecule? I talked about the concept of a group delay and how that arises from electron scattering phases. But this picture actually becomes a lot more complicated when you introduce the measurement itself. In order to measure the photoionization phase, you need to have an IR field, which is going to interact with the electron wave packet and induce extra measurement phases. So one of these is the continuum phase, which is quite nicely modeled for higher electron kinetic energies, but can get a little funny in the low energy threshold regime where I'm interested in studying molecular dynamics. So that makes it hard to talk about an electron scattering phase. You can also get partial wave coupling when you move to molecules, where the IR field couples all of the different molecular partial waves. And when we do all of our angular averaging to make this measurement, that also complicates the interpretation of the measurement. And once you throw in things like resonances, which happen in molecules and are interesting to study, you basically can't interpret this as a single photon ionization delay anymore. So instead, we like to talk about model discrimination for interpreting these measurements. Rather than literally talking about a time delay and what that means, we compare to theory at different levels of abstraction, turning interactions on and off, and trying to figure out what's really important in the time delay. So our model is a 2-color TDSE simulation of the rabbit measurement done by Vlad Serov and Anatoly Kifitz. What's nice about doing a 2-color simulation is that it kind of rolls all of these continuum coupling issues away. We can sweep it under the rug a bit and truly compare apples to apples when we talk about our experiment in theory if we simulate the full interaction. The interactions that we are changing and turning on and off here are the bond lengths of the H2 molecule. It's a clamped nuclei simulation, so the molecules hold still in one place, and the electron is ionized and scatters around that potential. And we did that for 3 different bond lengths that are close to the equilibrium position of H2 in order to simulate the correct electron kinetic energy of photoionization, which is very important for the photoemission delay, and also to look at different shaped potentials. So there's a expected general trend in the photoemission delay where the delay increases, gets a lot bigger with decreasing photoelectron energy. But there's also something sort of subtle and interesting going on in this calculation where the different bond lengths actually all lie on separate curves. This is kind of expected. They're different molecular potentials. It makes sense that they might have a different relationship to energy in their photoemission delay. But it's a demonstration of the fact that the dipole matrix element for the ionization changes pretty rapidly with R in the system. And we can't make the typical Frank-Condon approximation of pulling it out of the integral. Other groups have observed this in calculation, that the full extent of the nuclear wave packet is important to consider in H2. And you have to really consider the geometry of the molecule. However, these simulations don't include any nuclear motion. They're totally frozen. So these are geometric effects rather than dynamic effects in photoionization. If we compare our experiment in black to the theory now shown in red, there's a nice general agreement in the sort of global trend of photoionization delay versus electron kinetic energy. But we see some interesting deviations within the vibrational states. Zooming in here, the difference is most striking in sideband 12, which is the lowest kinetic energy, the closest to threshold ionization. The values start out pretty close together at the low vibrational states, but as we move up in vibrational state, which is the same as increasing the nuclear momentum, the discrepancy between the experiment and the theory really increases. You can see this trend mirrored in sideband 16, and it's also present to a lesser extent in sideband 14, in that the trend really deviates between experiment and theory as you go up in vibrational state. We believe that this is most likely caused by the nuclear motion, since that's the main phenomenon missing from the simulation and present in the experiment. One reason why we think this is because the discrepancy between experiment and theory can kind of be thought of as the nuclear electronic coupling term, since that's what's missing between them. And nuclear electronic coupling should increase with vibrational state or nuclear momentum, as it does here. And it should also increase as electron energy decreases and we get closer matching timescales. And we see that since the effect is more dramatic in sideband 12 than in sideband 16. So to conclude, photoemission delays are a sensitive probe for small variations in ionization dynamics. We see this since we can detect phase differences between the different vibrational states in H2. And the vibrational dynamics can affect the photoemission delay. We think that nuclear electronic coupling is a likely explanation, since this is the most significant term that is different between the experiment and theory, and also because of the way the trends deviate how nuclear electronic coupling should. This can, maybe be nicely explained as some sort of channel coupling phenomena where the electron interacts with the nuclei as it photoionizes and couples the different vibrational states of the cation. So I'd like to acknowledge the co-authors for this project, James and Phil, my supervisors, and Andrei Kamalov, who made this measurement with me, and the people who did the calculations, Anatoly Kifitz and Vlad Serov. I'd also like to acknowledge our funding from the US DOE Office of Basic Energy Sciences. Thanks, and thanks for having me.
Thank you, Li Wang, for this nice talk, and also for joining us given the time zone of Stanford. I mean, this is really a lot of effort from your side, so thank you. Thank you very much. And we are open for questions from the audience. If someone has anything to ask. Okay. In the meantime, I just have a couple of questions, so maybe we can start from that. The first one is that, okay, you're looking at H2 to look at the effects of, let's say, Born-Oppenheimer approximation breaking, because, okay, H2 is, the vibrational mode of H2 is very fast. And do you think there could be any way to see these effects also in other molecules, maybe more complex molecule, or?
Yeah, definitely. So other people have done vibrational state measurements in diatomics. There have been 2 studies in N2 looking at photoemission delays and vibrational states. I think it would be really interesting to look at maybe a molecule like NH3 with an umbrella mode. Just larger molecules with more interesting vibrational dynamics. Yeah. Obviously, we have to be like a little bit careful with rabbit because you end up with congested spectra and overlapping states that are difficult to disentangle. So target selection is really important. but maybe with streaking, you can do something a little more interesting. Of course, with streaking, you don't get the same electron spectral resolution, so that's a challenge.
Yeah, indeed, it is a challenge. And have you also tried maybe to play with this simple system H2, maybe instead of using hydrogen, using deuterium to see if it's changing something in the vibrational effects? Or
we haven't done that. That would be a really nice comparison.
Okay.
Since, yeah, it's been done for like HHE spectroscopy, and it shows really nice differences in the vibrational states, but we just didn't have any.
Okay. I see. Because that was the first thing that came to my mind when I saw your results. I mean,
that probably would have like been really nice to compare.
Yeah. Okay. Thank you. So I see there are no further questions from the audience. Okay. Okay, so indeed we have a question from Cattaneo, which is asking if you align in your experiment, you are aligning the molecules in the, so you're looking at the molecular frame, or you are just using isotropic gas?
Yeah, this is just isotropic.
Okay. So yeah, so maybe also aligning them could be another degree of freedom to add in the experiments.
Yeah, that would be interesting.
Okay, so I see no other questions from the audience. So thank you again for this nice talk, Anna. And we can go on with the last talk, which is an invited talk by Dr. Cattaneo. She completed her PhD in 2011 in Politecnico di Milano, and her PhD work was devoted to the fabrication and characterization of different nanostructures, from thin films to nanoparticles. And she continued her postdoc in the spectroscopy of solid and interfaces group at the University of Radboud in the Netherlands, and inside an international training network. And after that, she joined the group of Professor Ursula Keller at the ETH, where she performed many experiments on dynamical processes at the attosecond timescale, both in atoms and molecules. While since May 2020, she is running her own group at the Max Planck Institute of Heidelberg, and this group is devoted to the ultrafast dynamics in liquid crystals. So she will talk today about this work, in particular time resolved Hertz dynamics in liquid crystals, and the stage is yours, Laura.
Thank you so much. First question, can you hear me? I hope so.
Yes, we can hear you and we can see you.
Perfect. Okay, then I will share my screen and I hope everything will go smooth. So you are supposed to see, okay, my presentation, and then move to presentation mode. Yes. Do you see presentation mode?
Yes, everything works.
Perfect. Thank you so much. So indeed, I feel like a little bit off topic, although since until now, I was actually, thank you, back to my old time at ETH with ultrafast dynamics in diatomic molecules. Well, this is not easy. I can tell you, it's a hell of a job, but I wanted to go even more difficult with giant molecules, as you can see. And unfortunately, or fortunately, I don't know, I will be very complimentary because I will not be very atto today. I will be rather picosecond. But actually, this is a, let's say, preparing the ground towards atto. That can also be a way to say it. So then indeed, time resolved thermodynamics in thermotropic liquid crystal. And I will try to bring you in a journey today into this realm of soft matter, which is a bit unusual, and ultrafast. Ultrafast, of course, pico. I'm sorry. I will come as fast as I can to atto, but not yet. So the main motivation actually is to understand the collective dynamics in liquid crystal from pico down to femtosecond, and here we'll stop, a cross-phase transition, because this is the first step, indeed, first step towards atto, which means first step towards control, manipulation of the electronic properties of such material of liquid crystal, which actually more generally belong to the soft matter world. From a fundamental point of view, you can actually consider it as one of the basic steps we want always to do, actually, to understand light-matter interaction. And for me, it will mean actually to understand soft matter and light interaction at the ultrafast time scale. But from a more applied point of view, this actually can imply many things, because soft matter is very applied word, where we can see terahertz optical control, ultrafast soft photonic application, material where liquid crystal are currently used for electronic and ionic transport, and soft robotics. This is not something in the air, something that I'm actually speculating with. This is real applications that are ongoing right now, but still either static or very slow. So we can do something there. And indeed, I want to convince you that liquid crystal, or convince you, or at least explain you why I want to go with liquid crystal, because they are very unique model system from many points of view. Actually, the most obvious is because it's a mesophase. It's bringing together two phases, solid and liquid. In fact, one of the phases you might find in liquid crystal is not a material, it's a phase to be. Certain material present a liquid crystal phase. It's, for example, a nematic phase, where the molecule that compose the liquid crystal present no positional order, exactly like a liquid, but a long-range orientational order. And in fact, what I'm telling you is all about order. In fact, when you talk about liquid crystal, you cannot avoid analysis of order, which actually calls for orientation order parameter definition, which is actually the second coefficient of the polynomial, or the Legendre polynomial, defined as you see here from my pointer. And when you talk about, for example, a solid-like molecular solid, you might actually find the order the parameter equal to 1, because all the molecules are perfectly aligned along a main orientational direction, which is also called director. When you have a perfect liquid, you will have 0, because all the molecules are randomly aligned along any direction with respect to this axis. So there is no axis, basically. While in the nematic phase, for instance, you have an order parameter of about 0.7. So the liquid crystal, the molecule are almost all aligned. And actually this director you can consider as a macroscopic quantity that you can use, has his own dynamic, basically, on top of the usual hydrodynamic excitation. And it has a dynamic that falls into the nanosecond, sub-nanosecond time scale, mostly thermally driven. And as in the presentation of Lorenzo, is basically static for Attosecond cooking between. But still, it's moving. And I want to continue a little bit to describe you this system of liquid crystal, just to understand what the capability of this system can do. So we have a liquid, so its fluid is unable to support shear forces and forms droplets, but is also solid because it presents very peculiar properties of a condensed matter phase. So it's extremely birefringent, and it has very interesting electrical properties. And it arranges in a periodic manner in a different way. So you can have a wide range of different types of liquid crystal with different degree of organization and more or less close to a solid phase. We talk about nematic, these are the most liquid-like situation, where all the molecules are all aligned along one direction, but they have no positional order, only directional order. And you have a symmetric phase, where they are layered, and inside each layer, the molecule indeed can still move, but they maintain the same orientation and they don't cross layers. And you have chiral situation. You have even more chiral situation, I would say, here in the blue phase, or you have even columnar liquid crystal, where the molecules are rather circular than elongated. In this talk, I will actually only concentrate on very easy one, two type of the NCB family. So cyano-biphenyl. Cyano is this group where you have carbon-nitrogen group here. Biphenyl is these two groups of benzene rings, only with a single bond attached. And then you have an alkyl chain, which actually can change in length, either by 5 carbons, and then you have the very famous, I would say, 5CB, which is the most studied one, the easiest one, which forms only the nematic phase between the solid and the liquid, or also isotropic. It's called isotropic in the liquid crystal community. And it's also thermotropic liquid crystal because, as you see here, there is temperature. Indeed, in order to perform phase transition, you actually turn a knob on your heater, and that's it. And you can really easily control it. Or you can actually add 3 more carbon here at the tail, and then you have a osmotic configuration between solid and nematic. And here again, temperature. And now I want to show you what it means, phase transition from a nematic to isotropic. So now you see here it's progressing and temperature is rising from 22 to 35. And at a certain point, sorry, I don't have the temperature actually changing. Next time I will provide you. Here the phase transition is actually happening. It's progressing from one side to the other because of contact with the heater, which is actually not uniform. And then you see it's actually becoming liquid. And then I also, and this is really clear, while the phase transition for osmotic to nematic is actually kind of different, it's more subtle. So it's speed up, of course, because we have to do it very slowly. And then you start from a very uniform and almost stripy situation, which is not, it's not the layers that you see. I mean, this is really microscopically. And then, okay, it happened. You see a completely different version of your substrate. So it's actually becoming kind of more liquid, and it allows you to see the scratches basically on the surface of the cell. And this is exactly, I wanted to show you what it means to have a phase transition in a liquid crystal. Okay, now how I can conceive at all ultrafast in such material. So where we are actually liquid crystal, very well known for liquid crystal display. Everyone is looking into one. And now I want to bring you indeed in a journey of time scale and dynamics in liquid crystal, starting from the well-known millisecond at which liquid crystal are moving into the form exactly shape movements in the display you are looking into. And the movement that they are performing is actually called Frederick transition. It's a complete reorientation of the molecule by applying an external voltage. And this happens, in fact, in the millisecond time scale, perfectly fine for our eyes and gives very clean dynamics on the screen. A liquid crystal can go even faster, namely in the microsecond time scale. That was the first observation in the 80s when they were applying a nanosecond pulse to liquid crystal, and they were observing molecular dynamics in the microsecond, basically mostly induced by thermal reconfiguration of the hydrodynamics of the liquid crystal itself. In the nanosecond, actually, we can have fluorescence activity of the single molecule when the liquid crystal are diluted in solvents, and the 3 curves that you see here, the fluorescence is in the blue, in the visible, is determined by the different polarity of the solvent in which we were diluted. And so this actually changes the cage of molecules that can go around the liquid crystal itself and have either a red or a blue shift, depending on the type of interaction with the solvent itself. Or even recently kind of, let's say, in the 90s, they observed the possibility in 2013, they could see actually the modulation of the refractive index of liquid crystal in the nanosecond time scale by simply applying an electric field, a switch. And this was really ultra fast at that time because liquid crystal can switch this. And this is the same concept of the millisecond, but in nanoseconds. So this was already really ultra fast. And this was already kind of inspiring tips to say, hey, maybe this can go even faster, because they claimed that the limitation was simply the fact that the switch could not go faster, but liquid crystal was perfectly fine with that. So then we can look at the picosecond. What's happened in the picosecond time scale into liquid crystal? In the picosecond time scale, they could observe an amazing thing. Well, actually collective dynamics happening at fastest 100 picosecond. So we can say, okay, sub-nanosecond, but still. When actually converting a nazobenzene units, you can see here, this is a nazobenzene unit, and attaching two very long chains here, which makes the entire molecule a liquid crystal then. And then when shining with UV light, in order to have the classical trans to chins reconformation of the molecule, or isomerization, to happen very fast, faster than a single molecule itself can do. And they explain this effect like actually helped by the fact that the molecule was made to be a liquid crystal instead of just a nazobenzene unit. And there was actually another confirmation that liquid crystal can actually be ultra fast in a collective manner. What happens again in the real picosecond time scale, so talking about 1 to 2 picosecond, are librations. And actually, this is the main part of my talk today. So librations have been already observed in the 80s in liquid crystal, but they never been actually investigated, more than saying that whatever falls into 1 to 2 picosecond was actually nuclear nonlinear activity, which thermalizes within 2 picoseconds, and that's it. And I want to actually start from here. And in 2012, another group tried to see if liquid crystal, if we can translate picosecond in time scale in frequency, we go into terahertz. They saw that actually liquid crystal present, at least in what I call terahertz range, so in the really low terahertz, I will define it later. An interesting resonance or absorption behavior, let's say. So, and the two curves you see here are depending on the relative orientation of the liquid crystal. So the molecule, we're talking about 5 CB here, and showing you the structure again of the molecule with respect to the electric field of the terahertz pulse, which is impinging on it. And then we see very interesting features. And I want to actually give you an idea what is going on here, what's the kind of dynamics that those molecules are performing. And here you see actually the plot I just showed you. And hindering this part because we are not actually interested. We are interested in this low frequency region where it's not, where we actually could have been also theory support. So we are currently in collaboration with a group in Nijmegen, where Daria Galimberti specifically perform gas phase calculation for both 8 CB and 5 CB. And as you see, gas phase means single molecule. So it doesn't matter if it's a liquid crystal or not. So most of the feature can be actually reproduced here as a single molecule behavior. But is that it? Is that all we can actually say? So in the picosecond time scale, liquid crystal behave as a single molecule, or is that there is something more? Well, actually there is, in my opinion, something more, because most of the activity at 3 terahertz is actually not reproduced here in the single molecule. But I want to show you what can do this molecule. Oops. Okay, they are appearing by themselves. So yeah, okay, I showed them all. So what you see here, so we are actually sitting on here, or basically these two peak. This is exactly these two peak for the 5 CB and the 8 CB. this is the type of dynamics that this molecule, single molecule gas phase can perform. And here is also the type of dynamic that can perform at 4 terts, at about 4 terts for the 5CV and ACV. And this is exactly the type of link I would like to first address if these materials in the liquid crystal phase, not in the gas phase, are actually simply vibrating in a single molecule behavior, or there is something more, there is something that I can call collective. And it falls into the terts frequency spectrum. And what is missing here is the femtosecond part, which I actually said is just the beginning. And here, this is exactly the last part I would like to say. Let's say an outlook work that I want to go for. So liquid crystal, in fact, we cannot aim for really femtosecond dynamics of the entire molecule unless we talk about single bonds or hydrogen dynamics. Indeed, the liquid crystal has plenty of hydrogen atoms there. But we can think about electron dynamics there in the femtosecond. And actually, liquid crystal, for example, here you see this is a 5CB, naturally form excimer, as I already said before. So, and I normally do not order randomly, but I normally like to face and stack with the biphenyl one on top of the other. And this random formation of the excimer, whenever they actually get too close to each other, allows, for example, the formation of this excited state for very short time, the time along with these two molecules get in contact or close enough to get it. But when properly triggered with the resonant, let's say, pulse, which allows them to get close enough for enough time, will allow the, for example, first of all, formation of excimer and perhaps the promotion of an exciton. So to have not only charge migration across the molecule, but in between molecules too, and then become charge transfer. So that's exactly what I want to do, to actually now I'm in this step to actually get exactly knowledge about how I can control the nuclear dynamics in order to get second control on the electron dynamics in such material where I can impose a certain degree of order and then perhaps impose a certain degree of intermolecular dynamics. But for the moment, I'm looking for the nuclear dynamics, and this is the last inspiring work I've been doing actually before Ursula Keller experience, when I actually tried to pump simply with an 800 nanometer pulse of resonance liquid crystal, and then probe macroscopically the birefringence induced in the probe pulse from, interacting with the excited liquid crystal. And I could observe indeed ultrafast in the sub-picosecond time scale modification of the polarization of the probe beam, and a modification of this translates to modification of the refractive index of the liquid crystal itself in the femtosecond time scale. And it's translated into frequency was again 2.7 terahertz, which actually names for libration. And this was actually the first work where I could say, yes, I can go for ultra fast in liquid crystal. And this is exactly my goal. And to do so, actually, the next step indeed is not to use 800 anymore of resonance, but to use a terahertz pulse and then drive resonantly these collective modes in liquid crystal and see what's going on, to learn about intra and intermolecular dynamics, time and space coherence, and ultra-fast phase transition in case. And now I start with the technical part, what we need to do in order to have this measurement done. First of all, we have to work with liquid crystal. We prepare our liquid crystal cells in-house. So then we have an extensive cleaning procedure for surfaces because they have to get in contact with them. but not only, the surface has to be prepared in order to align the liquid crystal itself. So we need an extra polymer, which in our case we use polyvinyl alcohol to have a planar alignment of the liquid crystal and not homeotropic, let's say, and along a specific direction. So we managed to have a very uniform alignment depending on mainly on the, let's say, the spinning velocity of our spin coating process for this type of polymer. And then there is the building up of the cell itself, which requires a specific spacer and the filling in isotropic phase. And in the end, a sealing. And perhaps for this case, there was a bit too much sealing, but that's also fine. Because actually, for capillary forces are very strong with liquid crystal. If you don't seal it perfectly, you will not find any more liquid crystal in your cell after the first measurement or the first heating up and down in temperature. And here is our terahertz setup that we actually built up in order to have both the characterization of the terahertz itself by electro-optical sampling and the characterization of the sample when the nonlinear crystal for electro-optical sampling is not there. And for the generation, in order to have exactly the frequencies that we need, which means between 4 and 6 terahertz, which is a range which is exactly not so easy to get terahertz or intense terahertz pulses, we use an organic crystal, and then we have to pump it in at 1.4 micron, which calls for an optical parametric amplifier fed by 800 nanometer, 35 femtosecond and 9 millijoule, no, less than 9 millijoule pulses at 1 kilohertz. And what we use for detection indeed is, okay, a balanced photo detection in order to either measure the birefringence induced in the electro-optical sampling crystal for the terahertz cell, or the modification of the polarization of the probe when interacting with the sample. This is basically the same. But before going into the final results, I want to actually explain and give you a little bit more of a flavor of what terahertz, why terahertz is so interesting and why so nice to work with it. And it's actually the frequency which lies between microwave and infrared. You cannot see it, absolutely not see it, but you can feel it. I mean, it's actually kind of warm. In fact, energies, in terms of energies, is actually the same as a thermal energy, the milli-electron volts. Is the least explored spectral region, but nowadays I wouldn't say so, because there are many groups right now that are actually getting on board with terahertz. So since technologically wise equipment are there, and then it's becoming kind of spread out, the terahertz setups are actually getting more and more into many optical tables. And what I define terahertz actually is between, not, I mean, because I like it or because it's so important, but normally what is defined as terahertz is between 0.1 and 10. But still there is not a standard definition. What is the real terahertz, the region? And if I can give you a few numbers, indeed, we are in terms of wavelengths, we are talking about around hundreds of micron, or 1 terahertz is 300 micron. And then, as I said before, in terms of energy, is 1 terahertz is about 4 milli-electron volt. Which are the physical processes that happens in the terahertz? Well, actually, we have, as we see since this morning, rotational and vibrational energy levels. We have, as I actually showed you, large amplitude vibrational motion of organic compounds. We have phonons. I don't think I have to explain what is lattice vibration in solid. Then we have intraband transition in semiconductor, and we have also magnons. All this excitation happens in the terahertz spectral region, so few milli-electron volts. And then what I'm trying to do is actually link these two, between the large amplitude vibration motion and phonons. See if I can actually have a link in liquid crystal. Back again to our terahertz setup, and then when you measure your first terahertz pulse, basically you end up in time domain because the electro-optical sampling allows you to actually measure in time, and then so you can actually have intensity and phase, which is very important. You get this, and this is horrible. You say, oh my God, what is that? This is not terahertz. This is everything. But that actually is because terahertz doesn't require vacuum, but at least you need to purge your atmosphere because it's very sensitive to presence of water, because water is heavily absorbing those nice frequencies. And indeed, as soon as you get a purging box with dry air or nitrogen, then you got your almost clean terahertz pulse, which in frequency translate to this for our case and for the specific use of the crystal that we use. And the red, in fact, is actually instead the unpurged pulse, which mimic all the absorption lines of water you can use for checking or calibration even. And here is our measurement with liquid crystal indeed. So first we have our reference, so means that in our detection, we put our empty cell, and what we observe is simply a shift in time of the terahertz pulse, but not modified in the frequency content. And then when you put liquid crystal inside, you have both shift and modification of the frequency content, and then you can see the absorption in terahertz frequency, and we've managed to reproduce actually the results that they obtained in 2013, having only between 1 and 5 terahertz. And here we have 4 terahertz, exactly this big peak of absorption along the ordinary axis, and this kink at the extraordinary, and the 3 terahertz activity that is also been observed. And here are the time result family. So this is the time result by refringent measurement in crystal. So unfortunately, I don't have more to show you because we have been suffering a lot of down with laser, but at least it is something next time, promise, I will have much better results, but still something to discuss with. So this result has been obtained by pumping and probing along the ordinary axis of liquid crystal, so meaning this configuration, so liquid crystal aligned along one direction while pumping and probing perpendicular to it. So basically we are considering the response of the liquid crystal along the black line, when at 4 terahertz we have a big absorption. We are working with 5 CV, so the shorter one, which present only nematic phase and not schematic, and each color is a different intensity of our terahertz pulse, which at that time we could get only up to 240 kilovolt per centimeter. This is the voltage that we could get. And even though this is not that much, because we are aiming for megavolts centimeter, we could see already some saturation effect. And on top of saturation effect, we see some modulation. We keep them, and in gray, you see actually the terahertz pulse we used. And basically, after 1 picosecond, we can consider it finished. And here we see that this ringing of the signal keeps on going there, and then it loses itself in the noise. And basically, this is the first dynamic observation. I can say really the first dynamic observation in the terahertz in the picosecond time scale in liquid crystal. And we still have to analyze them. So theory didn't respond yet, but also from our side, we need to actually change configuration in terms of terahertz pumping compared to orientation of liquid crystal, and observation also at different angles, and change also temperature. So this was performed at, let's say, the crossover between solid and pneumatic. So we will have to do it as a function of temperature. And what do we expect as we increase the temperature, that all this ringing will completely disappear, and we will actually have simply cross-correlation response when the overlap is happening, and that's it. So with that, I would like to conclude to say with really few take-home messages, actually. The first one and big one is we have a long way to go. What we managed up to now, at least to have an idea of what we can expect when liquid crystal is a gas phase, and we want to go further and to understand when it's not in a gas phase, or in a liquid, let's say, but in a nematic phase, and how much we can push it in order to actually impose extra control on the nuclear part towards the electronic manipulation of electronic properties in liquid crystal. And I would like to do some acknowledgements. My current group is formed by Patrick here, which perform all the measurements that you see today. And Clara is actually working on another project in liquid crystal, which will be actually more up to, but still is pretty much a work in progress. If you're interested, I'm actually up to show you something. And some former members of the OCD, master students and visiting scientists. And also I would like to thank the theory that you saw today, provided by Daria Galimbecti from Aarhus University, which is still collaborating with us. And of course, I would like to thank you for your attention.
Thank you, Laura. Thank you for this nice presentation on such a diverse topic, let's say. With
yes.
But that's nice because, you know, you are expanding somehow the topic of the meeting also. So we are open for questions. Let's see if someone has them. Otherwise, I have a couple of questions. Okay, maybe I can start with mine. So I'm no expert whatsoever of terahertz and liquid crystals, but I was by looking at your, let's say, experimental setup, I see that your sample, your liquid crystals are like sliced in between two quartz plates, like
yes.
a panini kind of shape.
Yes.
Okay. And I was thinking about, since you're looking at, let's say, long delays with respect to femtoseconds rather than the picosecond regime, does the reflection of the terahertz inside these two slices play any role? Okay.
Yeah, absolutely.
So you can see it.
Yeah. You can see it. So I mean, there is a when you work with its frequency on the building up of your sample, it becomes a major time-consuming activity, I would say. And so, I mean, the choice of the material that you have to use has to be properly done, because otherwise you are actually lost in reflections. So your signal is constantly repeated in your timeline and you have a mess out of it. So first of all, you have to choose. So currently we are sitting, and especially since we are working in the 4 to 6 terahertz and not exactly 1 terahertz, for instance, where you might even have materials that has phonons in that region. First, material has to be transparent, and second, you have to have basically thicknesses that allows you to have basically far away back reflection, or and then have at least a window of clean signal.
Okay. So that seems like a lot of work to design, let's say, the correct sample holder. And we have also a question from Fernando, which is, which are the simplest molecules you can have in a liquid crystal, let's say, phase? Because this could be interesting for theory, especially if in a later stage you want to study some electron dynamics.
Exactly. So I guess the easiest, I exit from here and I can go to the structure, so then I can be a bit more explanatory. So here, if we look at this, so I was talking about indeed the, and come back here to the NCB series. So we can have NCB series basically starting from 2 NCB, but actually the 2 NCB is not presenting liquid crystal phase. I mean, it's actually presenting on there is only transition solid to isotropic. There is no liquid crystal. So let's say the one that can actually work a little bit can be 4. So oops, only one less. Oops, my mouth is actually doing very weird things. Sorry. I would say unfortunately, the smaller that for sure present nematic phase is this one. But for comparison, we can get, well, the only thing we can go is actually a bit shorter in this, but the biphenyl, but I mean, there is only there's also the biphenyl itself, but it's not nematic. It's not liquid crystal phase itself. So nematic 5CB is the smallest. As a model system for, let's say, having some electronic dynamics going on, I would say actually the group here that since basically mostly the optical properties of the liquid crystal come only from the biphenyl group, we might actually even try to have just the biphenyl going on and maybe just a piece, I mean, a stack of 2 biphenyl, one on top of the other could be already starting, in my opinion. Because then in theory, you can align like you want, like in a liquid crystal, and then get them close enough to mimic what we can impose with an external trigger into a liquid crystal phase.
Okay, nice. Thank you for answering from Fernando. And I have another question. So for now, phase transition of liquid crystal you're considering are always, let's say, triggered by temperature. But other, for example, liquid crystals that are triggered from other sources, I think maybe a static electric field can also trigger some, if I'm not mistaken. These are, let's say.
Static electric field actually, static electric field trigger reorientation, okay, which might also, by friction, induce some thermal, because maybe you have some, let's say, not perfectly well-conducting system, then you get little heat up, so then it can trigger phase transition. Confinement can actually induce phase transition, because if you think about a system like this, it's basically a quantized system in terms of layers. So whenever you have a system like this, for example, we are currently working on SMACTIC to get freestanding film, because surface tension is good enough to have freestanding films, and then the thickness of such freestanding film is exact, and integer numbers of these layers. Cannot be half of it, can be, so this is quantized. When you impose a quantized system to be confined, any other phase can show up, because maybe you frustrate the system so much that it cannot accommodate any more layers, and then you impose nematic in a temperature where it should lie, you could get SMACTIC, because it cannot simply accommodate this. And then this is one. But then you can actually come with when you come with a very intense trigger from outside, like a pulse at whatever frequency you are working, 800, I mean, 800 is very, let's say, big hammer. You might even break the molecules, then you don't have any more liquid crystal there. But then other, let's say, frequencies, you might impose a new order, and order means also phase, the type of phase you might impose on your system locally.
So let's see if there are other questions from the audience. I guess we have no more questions, so we can close here the session. So thank you, Laura, again for this nice talk, and good luck with your experiments, for your future plans about liquid crystals.
Thanks a lot.
And with this, the morning session is over. So now we will have a lunch break, and we can meet back here at 2 p.m. And the next session of the afternoon will be about correlated treatment of many-body dynamics. So thank you all again for joining this first Attochem Young Scientist Symposium, and see you in the afternoon session. Have a good lunch, everybody.